Every poison that made you. The complete history of Earth and life. So, here is something worth sitting with tonight. Take a slow breath in. Feel your lungs expand. Feel the air fill that warm space inside your chest, and then let it go. You have done that roughly 20,000 times today without thinking about it. And every single one of those breaths was made possible by the worst catastrophe life on Earth has ever inflicted on itself. The oxygen filling your lungs right now, that clear, invisible gas you cannot taste or smell, was once the most violent poison on this planet. About 2.5 billion years ago, when the first microorganisms started pumping it into the ancient oceans, oxygen tore through the existing biosphere like acid. It shredded cell membranes, it corroded DNA, it killed nearly everything alive. The creatures that had been quietly surviving for 1 billion years in an oxygen-free world were annihilated. Not by an asteroid or a supervolcano, but by the breath of their own neighbors. The first mass extinction in Earth's history was not caused by the planet, it was caused by life itself. And that oxygen, that poison, that killer of worlds, is now the only reason your brain has enough energy to process the words you are hearing. The same molecule. Poison and lifeblood. It depends entirely on when you showed up. Now hold that thought, because it turns out this is not a one-time trick. When you start looking at the full sweep of Earth's history, all 4.5 billion years of it, a pattern emerges that is so consistent, so stubbornly repetitive, that once you see it, you cannot unsee it. Every single catastrophe, every mass extinction, every planetary-scale disaster that nearly ended everything, turned out to be the necessary precondition for the next great leap forward. Every poison became a medicine. Every destruction cleared the ground for something more complex, more resilient, more astonishing than what came before. The collision that nearly shattered the young Earth into rubble gave us the moon, the anchor that stabilizes our axis and makes seasons possible. The global freeze that entombed the entire planet in ice for millions of years, a frozen prison from pole to pole, created the conditions for multicellular life to finally emerge. The volcanic apocalypse that killed 96% of all species, the closest life has ever come to total annihilation, opened the door for a new dynasty of creatures that would rule the Earth for 160 million years. And when a rock from deep space ended that dynasty in a single afternoon, the terrified little mammals hiding in underground burrows finally got their chance. And one branch of those mammals, millions of years later, would learn to stand upright, to make tools, to control fire, to speak, to wonder about the stars. Every step on the road to you runs through a catastrophe. Every chapter of this story begins with something terrible and ends with something that should have been impossible. And that raises a few questions that I think are worth carrying with you tonight. Why does destruction create? Why does every ending in Earth's history seem to seed a new beginning that is grander and stranger than what came before? Is there something about catastrophe itself, about the act of tearing down, that is necessary for complexity to emerge? Could any of this have happened without the disasters? Could life have reached the same heights through slow, steady progress without the extinctions, without the ice ages, without the collisions? Or is the destruction somehow the engine, the thing that forces life to reinvent itself, to find solutions it would never have stumbled upon in calmer times? And here is the question that might follow you into sleep. If every poison in Earth's past became a medicine, if every catastrophe turned out to be a doorway, then what does that mean for us? Right now, in this century, humanity is doing something to this planet that has no precedent. We are changing the atmosphere faster than any volcanic eruption in Earth's history. We are driving species extinct at a rate that rivals the great mass extinctions. We are, in a very real sense, the latest poison. The question is whether we are also the latest medicine. Whether the pattern holds, whether this story has one more impossible twist left in it. But we are getting ahead of ourselves. Tonight, we are going to walk through the whole thing, all 4.5 billion years, slowly, carefully, one catastrophe at a time.
We are going to watch this planet get destroyed and rebuilt over and over. And we are going to trace the thread that connects every one of those disasters to the body you are resting in right now. Because every atom in that body has a story. And every one of those stories begins with something that should have ended everything. Let's start at the very beginning. Before there was a planet. Before there was an ocean. Before there was even a solid surface to stand on. Let's start with the first poison. Chapter 1. The first poison. Collision. 4.5 billion years ago, there was no Earth. Not yet. Where you are lying right now, there was nothing but a slowly rotating disk of gas and dust. A vast cloud of debris, left over from the formation of the sun. The sun itself was young, barely ignited, a newborn star just beginning to fuse hydrogen in its core.
And around it, in that flat, swirling disk, trillions of tiny particles of rock and ice and metal were doing what gravity always makes particles do. They were bumping into each other, sticking together, growing. Think of it like a snowball rolling downhill, except the snowball is made of molten rock and the hill is 4 billion miles wide. Small grains stuck to form pebbles. Pebbles clumped into boulders. Boulders crashed together to build objects the size of mountains. And those mountain-sized chunks, called planetesimals, kept colliding, kept merging, kept growing, each impact adding more mass, more heat, more gravitational pull, which attracted still more material, which caused still more collisions. The early solar system was a demolition derby. Dozens of protoplanets jostled for space in overlapping orbits, constantly smashing into each other, spraying debris, reforming, smashing again.
And out of that violence, about 4.5 billion years ago, one of those growing bodies crossed a threshold. It became massive enough for its own gravity to pull it into a roughly spherical shape. It had swept up most of the debris in its orbital lane. It was not yet a planet in any sense you would recognize, but it had a claim on the space it occupied. It was the proto-Earth. And it was a nightmare. The entire surface was a churning ocean of molten rock. Not water, rock. Temperatures exceeded 3,600 degrees Fahrenheit. The magma glowed white and orange, bubbling and surging in slow convective currents. There was no solid ground anywhere. If you could somehow hover above this world, you would see a sphere of liquid fire, dimly lit by a hazy sun through a sky choked with vaporized silicates, sulfur compounds, and carbon dioxide so dense and hot that it pressed down on the surface like a physical weight.
Scientists call this period the Hadean Eon, named after Hades, the Greek god of the underworld. The name is not poetic exaggeration. The early Earth was genuinely, measurably, a vision of hell. But hell was about to get worse. Somewhere in the inner solar system, another protoplanet had been growing in a nearby orbit. It was smaller than Earth, roughly the size of Mars, a body perhaps 4,000 miles across. Astronomers have given it a name borrowed from Greek mythology, Theia, the mother of the moon goddess Selene. And the name turned out to be oddly prophetic, because what Theia was about to do would create the moon. For millions of years, Earth and Theia had been drifting closer, their orbits slowly converging through gravitational perturbations from Jupiter and the other growing planets. There was no drama in the approach, no visible countdown, just the silent, patient arithmetic of gravity, nudging two massive objects into an intersection that neither could avoid.
And then, roughly 4,450,000,000 years ago, they met. The collision between Earth and Theia released energy on a scale that is genuinely difficult to comprehend. The force of impact was billions of times greater than the most powerful nuclear weapon ever detonated. When Theia struck, it was not like two billiard balls bouncing off each other. Both bodies were partially molten. The impact speed was perhaps 25,000 miles per hour. At those velocities, rock behaves like liquid. The two worlds did not so much collide as merge, violently, catastrophically, their outer layers exploding outward in a spray of vaporized rock and superheated plasma, while their dense iron cores sank toward a common center. The impact knocked Earth's rotational axis into a tilt, roughly 23.5 degrees from vertical. Theia's iron core plunged deep into the Earth and fused with Earth's own core, dramatically increasing the size and heat of our planet's metallic heart. And the debris, trillions of tons of molten rock and gas blasted into orbit, formed a glowing ring around the wounded Earth, a ring that over the following centuries, through the same gravitational clumping that built the planets, coalesced into a single large body, the Moon. In those earliest days, the Moon hung in Earth's sky far closer than it does now, perhaps 10 times closer. If you could have looked up through the hellish atmosphere, you would have seen a vast orb of glowing rock filling a huge portion of the sky, its surface still running with rivers of lava, casting a dull red light over the molten Earth below. Over billions of years, tidal interactions would slowly push the Moon further away, to the distance we see it today, about 239,000 miles. It is still receding, even now, by about 1.5 inches per year. But the Moon's distance matters far less than what it does. The Moon's gravitational pull acts as an anchor. It stabilizes Earth's axial tilt, keeping it locked at that roughly 23.5 degree angle instead of allowing it to wobble chaotically over millions of years. Mars, which has no large moon, suffers exactly this fate. Its axial tilt has varied wildly over its history, swinging from nearly 0 degrees to over 60, producing catastrophic climate swings that may have prevented any complex life from gaining a foothold. Earth, thanks to the Moon, has had a relatively stable tilt for billions of years. That stability gives us predictable seasons. Predictable seasons give ecosystems time to adapt, to specialize, to build complexity. And the tides. The Moon's gravity pulls on Earth's oceans, creating tidal cycles, the rhythmic advance and retreat of water along every coastline. Those tides would turn out to be far more important than anyone could have guessed. Billions of years later, in shallow tidal pools, where seawater repeatedly washed over rocks and then receded, the wet-dry cycles would play a crucial role in concentrating the chemical building blocks of life, helping simple organic molecules link together into longer, more complex chains. Without tides, without that rhythmic washing, the chemistry of life's origin might never have gotten started. Think about what that means. The most violent event in Earth's history, a collision so powerful it nearly destroyed the planet entirely, turned out to be the single most important gift the young Earth ever received. Without Theia, no moon. Without the moon, no stable axis. Without a stable axis, no predictable climate. Without a predictable climate, no complex life. Without tides, perhaps no life at all. And there is something else happening during this long cooling period that deserves attention, because it connects directly to the question of how improbable your existence really is. As the Earth cooled and the first solid crust began to form, the planet's interior was organizing itself in a way that would turn out to be crucial. The dense iron core, swollen by the addition of Theia's iron, was separating into two distinct layers. The innermost part, under unimaginable pressure, solidified into a ball of solid iron roughly the size of the moon. But around it, a thick shell of liquid iron remained molten, churning in slow convective currents, driven by the heat escaping from the solid core below. Those currents of liquid metal, flowing through a rotating planet, generated something invisible but essential: a magnetic field. The Earth's magnetic field extends tens of thousands of miles into space, forming a protective bubble called the magnetosphere. And that magnetosphere does something that no amount of atmosphere alone can do. It deflects the solar wind. The solar wind is a constant stream of charged particles, protons and electrons, blasting outward from the Sun at hundreds of miles per second. On a planet without a magnetic field, those particles slam directly into the upper atmosphere, slowly stripping it away. Mars once had a thicker atmosphere and possibly liquid water on its surface. But Mars is smaller than Earth, its core cooled faster, and its magnetic field died. Without that magnetic shield, the solar wind stripped Mars of most of its atmosphere over hundreds of millions of years. And whatever water existed on the surface evaporated into space. Mars became the cold, barren desert we see today. Earth kept its magnetic field, and because it kept its magnetic field, it kept its atmosphere. And because it kept its atmosphere, it kept its oceans. And because it kept its oceans, life had a place to begin, and a medium in which to evolve for 4 billion years. So the collision with Theia gave the Earth not one gift, but 3. The moon, which stabilized the axis, the enlarged iron core, which powered the magnetic field, and the magnetic field, which protected the atmosphere and the oceans from being stripped away by the Sun. 3 consequences of one act of planetary violence, each of them essential, each of them the difference between a living world and a dead one. The first poison was collision, total, apocalyptic, planet-shattering collision. And the medicine was everything that followed. Now, there is something else I want you to hold in your mind as we move forward. After the impact, after the moon formed, the Earth was still a molten wasteland, still a glowing ball of magma under a poisonous sky. But something was beginning to change. The cold vacuum of space was slowly, relentlessly pulling heat away from the surface.
Degree by degree, century by century, the Earth was cooling. Volcanoes, thousands of them, were erupting constantly across the surface, tearing through the thin, cracking crust. And with every eruption, they were belching enormous quantities of gas into the atmosphere. Carbon dioxide, nitrogen, sulfur dioxide, and, crucially, water vapor. Water that had been locked inside the planet's rocks since the very beginning, water delivered by comets and asteroids that continued to bombard the cooling world. All of that water was accumulating in the thickening atmosphere, forming vast, heavy, planet-spanning clouds. And then, somewhere around 4 billion years ago, the surface temperature dropped below a critical threshold. Below 212 degrees Fahrenheit, below the boiling point of water. The first raindrop in Earth's history fell onto hot rock and instantly evaporated. But more drops followed, thousands, millions, billions. A rain began that would not stop for millions of years. Water cascaded from the sky in unimaginable volumes, flooding across the dark volcanic plains, pooling in craters and basins, dissolving minerals and salts from the cooling rock. Rivers of acidic, mineral-rich water carved channels across the barren surface and poured into the lowest places. When the rain finally eased, Earth had been transformed. The hellfire was extinguished. The planet's surface, for the first time, was covered in liquid water. A vast, globe-spanning ocean, dark green or murky brown from dissolved iron, under a sky still heavy with carbon dioxide and tinged a deep, unsettling orange. There were no continents as we know them, just scattered volcanic islands poking above the waves, and everywhere else, water. Warm, acidic, mineral-laden water stretching to every horizon. The stage was set. Earth had endured its first poison and survived.
The collision that should have ended everything had instead given the planet a moon, an ocean, and a chance. But nothing was alive. Not yet. The ocean was a vast, dark, silent body of water on a planet that had no audiences, no witnesses, no creatures of any kind to notice its existence. Earth was, by every reasonable measure, a dead world with warm water. And yet, if the collision had never happened, there would be no moon, no stable axis, no magnetic shield, no atmosphere, no ocean. The most violent event in the young solar system had built the only home life would ever know. The first answer to our question was already here. Destruction did not merely precede creation, it provided the raw materials. And somewhere in the deepest, darkest part of that ocean, where no sunlight could reach, where the crushing pressure of miles of water pressed down on a cracked and restless seafloor, something was about to happen. Something so quiet, so microscopic, so impossibly unlikely that 4.5 billion years later, we still argue about exactly how it worked. Life was about to begin, and it would immediately start changing the planet. Because on this world, life would turn out to be the most dangerous thing that ever happened. Chapter 2. The second poison. Breath. Let's go down together. Down through that ancient ocean, through the murky greenish water, past the dim zone where the last traces of sunlight fade. Down through hundreds of feet of increasing cold and pressure. Down to the floor of the primordial sea. It is absolutely dark here. There is no light from the sky, no bioluminescence, because there is no life yet to produce it. Only darkness and the faint grinding sounds of a planet's crust still settling, still cracking, still adjusting to the tremendous forces beneath it. And then, in that darkness, you begin to see a glow. Not sunlight, something else entirely. Along a ridge where the ocean floor has split open, superheated water is blasting upward from fissures in the rock. This water has seeped down through cracks in the crust, encountered magma chambers deep below, been heated to 600, 700 degrees Fahrenheit, and been shot back up in pressurized jets. The water is so hot, it shimmers. It carries dissolved minerals, iron, sulfur, manganese, hydrogen sulfide, and when it hits the frigid seawater, those minerals settle out instantly, forming towering chimneys of dark mineral deposits. Scientists call them hydrothermal vents. The dark ones, rich in iron and sulfide, are called black smokers. These vents are churning out a constant stream of chemical energy. Hot, mineral-rich fluid meets cold, mineral-poor water. And at that boundary, at that interface between two very different chemical environments, there is energy to be harvested.
Gradients of temperature, gradients of pH, gradients of chemical concentration, and energy flows along gradients the way water flows downhill. And it is here, at this boundary, in this narrow zone between scorching and freezing, that something extraordinary began. Nobody knows exactly how. That needs to be said honestly, because the origin of life is one of the deepest unsolved problems in all of science. We have hypotheses. We have experiments that show how individual pieces of the puzzle could have formed. We have Stanley Miller's famous experiment from 1953, where he sent electric sparks through a mixture of gases meant to simulate the early atmosphere, and produced amino acids, the building blocks of proteins. We know that fatty acids can spontaneously form tiny hollow spheres, membranes, in water.
We know that RNA, a molecule closely related to DNA, can, in certain conditions, catalyze its own replication, acting as both information carrier and chemical engine simultaneously. But the full sequence, the precise chain of events that took simple chemistry and turned it into biology, that took molecules and made them alive, remains one of the great open questions. What we do know is that it happened, and the evidence strongly suggests it happened in an environment very much like these hydrothermal vents. Deep, dark, hot, chemically rich, and sheltered from the ultraviolet radiation that was bathing the unprotected surface. Sometime around 4 billion years ago, give or take a few 100 million years, the first living cell appeared on Earth. It was unimaginably simple. A tiny bag of chemicals enclosed in a thin lipid membrane, smaller than anything you could see with your naked eye. It had no eyes, no brain, no limbs, no sense organs of any kind. It was just a small, fragile pocket of organized chemistry in a vast ocean of disorganized chemistry. But it could do something that no rock, no mineral, no ocean current, no volcano could do. It could make a copy of itself. It could take raw materials from its environment, rearrange them according to instructions encoded in its own molecular structure, and produce a second cell nearly identical to the first. And that second cell could do the same, and the third, and the 1,000th. This ability, self-replication, is the dividing line between chemistry and biology. On one side of that line, you have interesting molecules floating in warm water. On the other side, you have life. And once that line was crossed, once the first self-replicating cell existed, the rules changed forever. Because replication is not perfect. Copies contain errors, mutations, and mutations mean variation. And variation, in a world where resources are limited and conditions are harsh, means competition. And competition means that the variants best suited to their environment survive and reproduce more, while the less suited variants fade away. Evolution by natural selection had begun. Not as a theory, not as an idea, as a physical process running automatically in the dark at the bottom of an ancient ocean, with nobody watching. And here, in this quiet stretch of Earth's early history, the planet and life were already beginning that conversation, that back and forth exchange of transformations that would define the rest of the story. Life was changing the chemistry of the ocean, consuming certain compounds and producing others, altering the pH and mineral composition of the water around it. And the ocean, in turn, was shaping life, selecting for organisms that could tolerate its particular chemistry, rewarding adaptations that exploited the available resources, punishing strategies that could not cope with the conditions. Even the geology was part of this exchange.
Plate tectonics, that slow grinding process by which the Earth's crust moves in great slabs, was reshaping the ocean floor, opening and closing basins, building volcanic islands, subducting old crust beneath new. The movement of the plates carried chemicals from the deep mantle to the surface and pulled surface minerals back down. The composition of the ocean changed over hundreds of millions of years as different minerals were cycled through the system, and life had to adapt to each shift, each new chemical regime. This was not a static world with static inhabitants. It was a dynamic system, geology and biology intertwined, each one altering the conditions that the other faced. The Earth shaped life. And life, in ways that were still subtle and small at this stage, was beginning to shape the Earth. The cyanobacteria would be the first organisms to demonstrate just how dramatically biology could alter the planet.
But even before them, the simple chemical activities of billions of bacteria were subtly modifying the chemistry of the oceans and the composition of the sediments. Life was leaving fingerprints on the rocks, chemical signatures that geologists can still read today, 4 billion years later. And then, for a very, very long time, almost nothing seemed to happen. This is the part of the story that most popular accounts rush through. And I think that is a mistake, because the scale of time involved here is genuinely staggering, and it matters. From the origin of life, roughly 4 billion years ago, until about 2.5 billion years ago, life on Earth consisted entirely of single-celled organisms, bacteria and archaea, microscopic, invisible to the naked eye, floating in the ocean, clinging to rocks, clustered around hydrothermal vents. That is 1.5 billion years. 1.5 billion.
To put that in perspective, the entire history of complex multicellular life on Earth, from the first animals to the dinosaurs to the rise and fall of every human civilization, fits into roughly the last 600 million years. The bacteria had the planet to themselves for more than twice that long, more than twice the entire span from the Cambrian explosion to this moment. And they were not doing nothing during that time. Evolution was working, slowly, relentlessly. Different lineages of bacteria were exploring different chemical strategies for survival. Some learned to extract energy from hydrogen sulfide. Some learned to metabolize iron. Some found ways to thrive in boiling water, in freezing water, in water so acidic it would dissolve metal. Life was diversifying, adapting, filling every niche the planet offered. But it was all invisible, all microscopic. If you had visited Earth during this long, quiet era, you would have seen what appeared to be a completely dead planet, an ocean under a hazy orange sky. Barren volcanic islands, no green, no movement, no sound except the wind and the waves. The greatest revolution in the history of the universe. The emergence and diversification of life was happening entirely out of sight. And then, somewhere around 2.5 billion years ago, one lineage of bacteria stumbled onto something new, something that would change the planet more profoundly than any asteroid or supervolcano ever could. They learned to eat sunlight. Now, let me be clear about what this means because it is easy to gloss over, and it deserves your full attention. Before this moment, all life on Earth depended on chemical energy, the energy locked in molecules like hydrogen sulfide or dissolved iron. These energy sources were real. They were abundant in certain places, but they were limited. Hydrothermal vents are scattered. Chemical nutrients in the ocean are finite. Life was tethered to the places where chemistry provided fuel.
But sunlight is everywhere. It falls on every square foot of the ocean's surface, continuously, in staggering quantities. If you could tap into that energy source, if you could capture photons and use their energy to drive the chemical reactions of life, you would have access to a power supply so vast, so inexhaustible, that it would dwarf everything else combined. The bacteria that figured this out are called cyanobacteria, and the process they invented is called photosynthesis. Using a green pigment called chlorophyll, they could absorb photons of sunlight and use that energy to split molecules of water and carbon dioxide, rearranging the atoms to build sugars, which stored the energy in chemical form for later use. It was, and remains, one of the most elegant pieces of molecular engineering in all of biology. Cyanobacteria did not stay in the deep ocean. They rose to the surface, to the sunlit upper waters, where their new ability gave them an overwhelming advantage.
They multiplied with extraordinary speed. They spread across the oceans, forming vast mats and films on every available surface, carpeting shallow seafloors, coating rocks, turning the upper ocean into a living green skin. And as they ate sunlight and built sugars, they produced waste. Every industrial process has waste. Every factory has an exhaust pipe. And the exhaust of photosynthesis, the leftover atom that cyanobacteria had no use for after splitting water molecules, was oxygen. Now here is where the story takes its darkest turn since the collision with Theia. Because you need to understand what oxygen meant to the world that existed before cyanobacteria. For the first 1.5 billion years of life on Earth, the atmosphere and oceans contained essentially no free oxygen. Life had evolved in an oxygen-free world. Every biochemical pathway, every metabolic process, every molecular mechanism that kept cells alive had been designed, through billions of years of evolution, to function without oxygen. And not just without it. For these organisms, oxygen was actively dangerous. Oxygen is a highly reactive gas. That is actually why it is so useful to us, because its reactivity allows it to participate in the energetic metabolic reactions that power our cells. But that same reactivity makes it a potent destroyer of organic molecules. It attacks cell membranes, it damages DNA, it oxidizes the delicate molecular machinery inside cells. For the anaerobic organisms that had been running the show for over 1 billion years, free oxygen was not a neutral substance. It was a lethal toxin. And the cyanobacteria were pumping it into the ocean by the billions of tons. At first, the oxygen did not accumulate. The ocean was full of dissolved iron, and iron reacts readily with oxygen, forming iron oxide. Rust.
For hundreds of millions of years, every molecule of oxygen that the cyanobacteria produced was immediately soaked up by dissolved iron, forming tiny particles of rust that sank to the ocean floor. Layer upon layer of iron oxide accumulated on the seabed, building up deposits that would later become the banded iron formations, those striking red and black striped rock layers that geologists find all over the world today. Every time you see a piece of banded iron, you are looking at the chemical record of the oxygen slowly saturating the ancient ocean, one layer at a time. Let me paint a picture of what this looked like, because the physical evidence is still visible today, and it is beautiful in a haunting way. If you travel to the iron ranges of northern Minnesota, or the Pilbara region of Western Australia, or the ancient rocks of South Africa, you can see the geological record of the oxygen catastrophe with your own eyes. The banded iron formations are layers of rock alternating between red-orange bands of iron oxide, the rust, and darker bands of silica and other minerals. Each band represents a period of oxygen production by cyanobacteria, followed by a period of chemical reaction as that oxygen was absorbed by dissolved iron. The alternating pattern, red and dark, looks almost like the pages of a book, and in a sense, that is exactly what it is. A book written by the first great war between life and chemistry, readable 4 billion years later by anyone willing to look. Those banded iron formations are not just geological curiosities, they are the source of most of the iron ore that humans mine today. The steel in the buildings around you, the iron in the bridges you drive across, the metal in your car and your refrigerator, and the structural beams of your house. Almost all of it comes from iron that was deposited on ancient ocean floors by the metabolic waste of cyanobacteria over 2 billion years ago. The infrastructure of modern civilization is literally built from the byproducts of the oxygen catastrophe. And the iron in your own blood. The hemoglobin molecules in your red blood cells, each one containing 4 iron atoms at its core. The molecules that carry oxygen from your lungs to your tissues and carbon dioxide back again. That iron was processed through the same ancient cycle. It was dissolved in the primordial ocean, oxidized by cyanobacterial oxygen, deposited as banded iron, buried, compressed into rock over billions of years, mined by humans, smelted and incorporated into the manufactured world around you, or absorbed as a nutrient by the plants and animals you eat, and built into the hemoglobin that is right now carrying oxygen through your bloodstream. The iron in your blood is ancient. It connects you directly to that moment, 2.5 billion years ago, when the ocean turned red with rust and almost everything alive was dying from the breath of its neighbors. But eventually, after hundreds of millions of years of continuous oxygen production, the dissolved iron ran out. There was no more iron left to absorb the oxygen, and the excess began to leak. First into the upper ocean, then, bubbling up through the water column, into the atmosphere. The great oxygenation event. Geologists capitalize it because it deserves capitals. It was, by any measure, one of the most transformative events in the history of the planet. As free oxygen flooded the oceans and seeped into the air, it hit the existing biosphere like a wall of acid. Anaerobic organisms that had thrived for billions of years found themselves suddenly immersed in a substance that destroyed their cellular machinery. The die-off was catastrophic. We do not have fossil evidence detailed enough to know the exact percentage of species that perished, but the consensus among scientists is that the Great Oxygenation Event caused the first mass extinction in Earth's history, and possibly the most severe one in proportional terms. An entire biosphere, built over 1.5 billion years, was largely dismantled by a waste product of its own neighbours. And the killing did not stop with biology. Oxygen in the atmosphere immediately began reacting with methane, a powerful greenhouse gas that had been helping to keep the early Earth warm.
Methane is many times more effective than carbon dioxide at trapping heat, and when oxygen broke it down, the atmospheric methane concentration plummeted. Imagine pulling a thick blanket off a sleeping body on a freezing night. That is roughly what happened to Earth's climate. The methane blanket was destroyed. The greenhouse effect weakened dramatically, and the planet's temperature began to fall. But we are getting ahead of ourselves. We will follow that thread in the next chapter, because the consequences of the oxygen catastrophe, the freezing of the entire planet, deserve their own space. For now, I want you to sit with the central paradox of this chapter. The second poison was oxygen, the breath that keeps you alive right now. The molecule that powers every thought you are thinking, every heartbeat your chest is producing, every process in your body that distinguishes you from a stone. Oxygen did not start as a gift.
It started as a weapon of mass destruction, the deadliest pollutant in the history of this planet, released by organisms that had no idea what they were doing. Organisms that were just trying to eat sunlight and happened to produce a waste product that killed almost everything else alive. And yet, if the cyanobacteria had never evolved, if oxygen had never flooded the atmosphere, then the entire trajectory of complex life on Earth would have been impossible. Because the metabolic pathways that use oxygen to generate energy, aerobic respiration, produce roughly 18 times more energy per molecule of glucose than the old anaerobic pathways. 18 times. Complex, multicellular organisms, creatures with muscles and nervous systems and brains, have enormous energy demands. They simply cannot run on the old anaerobic chemistry. They need oxygen. You need oxygen. Every animal on this planet needs oxygen. The poison that killed the old world was the fuel that built the new one.
And here is something else worth holding. In the aftermath of the oxygen crisis, deep in the oceans where some oxygen was now present but conditions were still harsh, something happened between two cells that would turn out to be just as consequential as photosynthesis itself. A larger cell, probably an archaean, engulfed a smaller bacterium. This happened constantly in the microbial world, cells eating other cells, predation at the microscopic scale. Normally, the engulfed cell would be digested, broken down, its molecules repurposed as food. But this time, the smaller cell did not die. Whether by accident, by some quirk of membrane chemistry, by some mutation that prevented digestion, the smaller bacterium survived inside the larger cell. It continued to live. It continued to function. And the thing it could do, the thing the larger cell could not do on its own, was use oxygen with extraordinary efficiency to generate energy. The larger cell provided shelter, a stable internal environment, protection from the harsh outside world. The smaller cell provided a constant, abundant supply of energy. And over time, over millions of years, this arrangement became permanent. The smaller cell lost its ability to live independently. The larger cell became dependent on the energy its internal partner provided. Two separate organisms merged into one. A new kind of cell was born, more powerful than either of its parents. That smaller bacterium, trapped inside its host, eventually became what we now call a mitochondrion. And the cell that resulted from this merger, a cell with an internal power plant, became the ancestor of all eukaryotic life.
Every animal cell, every plant cell, every fungal cell on Earth today carries mitochondria. You have roughly 37 trillion cells in your body, and every single one of them contains hundreds or thousands of mitochondria, tiny descendants of a bacterium that was swallowed and never released roughly 2 billion years ago. Think about that tonight. Right now, as you lie still, trillions of tiny structures inside your cells are burning oxygen to make energy, keeping you warm, keeping your brain running, keeping your heart beating. And each one of those structures was once a free living organism. You are not a single creature. You are a collaboration, an ancient partnership between two kinds of cells that learn to live together instead of consuming each other. So here was the pattern again. A catastrophe, the worst mass extinction the world had ever seen, followed by something that could not have existed without it. The second poison gave the world two gifts. It gave it oxygen, the fuel of complex life. And it gave it the first great act of cooperation, the merger that created the eukaryotic cell, the building block from which every animal, plant, and fungus on Earth would eventually be built. But the immediate aftermath of the oxygen catastrophe was not cooperation. It was cold. Unimaginable, world-ending cold. Because when the methane blanket was stripped from the atmosphere, the Earth began to freeze. And what happened next was the most extreme climate event in the planet's entire history. The third poison was about to descend. Chapter 3. The third poison. Ice. Try to picture what happened to the Earth after the oxygen crisis stripped away the methane greenhouse. And I mean really picture it, because the scale of this event is something that most people have never heard of, and when they do hear about it, they tend to assume it is an exaggeration. It is not. As methane levels in the atmosphere dropped, the planet's ability to trap heat collapsed. Global temperatures fell. Ice began to form at the poles, which was not unusual. Earth has had polar ice many times in its history. But this time the cooling did not stop at the poles. The ice crept toward the equator, and as it spread, something terrible happened. Ice is white. Open ocean is dark. Dark surfaces absorb sunlight and convert it to heat. White surfaces reflect sunlight back into space. So as the ice advanced and covered more of the ocean, the planet reflected more sunlight, which made it colder, which caused more ice to form, which reflected even more sunlight, which made it even colder. A feedback loop, a self-reinforcing spiral of freezing. Each degree of cooling produced more ice, and more ice produced more cooling. There is a tipping point in this process, a threshold beyond which the loop becomes unstoppable. Once the ice sheets reach roughly 30 degrees latitude, about a third of the way from the poles to the equator, the feedback becomes so powerful that nothing on the surface can reverse it. The ice charges toward the equator with the inevitability of a mathematical equation. The entire planet froze. Not partially, not mostly, entirely. From the North Pole to the South Pole, from the deepest ocean trenches to the highest volcanic peaks, the Earth was entombed in ice. The oceans, those vast bodies of water that had been home to every living thing for over 1 billion years, were sealed beneath a shell of ice that may have been half a mile thick or more. The surface temperature plummeted to roughly -60 degrees Fahrenheit, colder than the interior of Antarctica today. The sky was a pale, featureless white. The wind screamed across endless plains of ice that reflected the weak sunlight with blinding intensity. Scientists call this snowball Earth, and it happened not once, but at least twice, possibly more, between roughly 720 million and 635 million years ago. The Sturtian glaciation lasted perhaps 57 million years. The Maranoan glaciation, which followed after a brief warm interlude, lasted roughly 15 million years. 15 million years of unbroken planetary freezing. Think about what that means for life. By this point in Earth's history, life had been evolving for well over 2 billion years. Bacteria had diversified into thousands of lineages. Cyanobacteria were still photosynthesizing, still producing oxygen. The great endosymbiosis had already occurred, producing the first eukaryotic cells with their mitochondrial power plants. These eukaryotic cells were beginning to explore new possibilities, growing larger, developing more complex internal structures. And then the ice came down, and all of it was sealed away. No sunlight reached the ocean through half a mile of ice. Without sunlight, photosynthesis stopped. Without photosynthesis, the base of the food chain was severed. The vast majority of living things on the planet died. Not from the cold directly, though that killed many, but from starvation, from the collapse of the energy supply that had sustained life for billions of years. And yet, life did not go extinct. In the deepest parts of the ocean, far below the ice, where the seafloor still cracked and shifted, hydrothermal vents still pumped hot, mineral-rich water into the darkness. Those vents, the same kind of environment where life may have first begun, became arcs. Tiny communities of bacteria and archaea clustered around the vents, feeding on chemical energy, completely independent of sunlight, surviving in the one place where the planet's internal heat could keep them alive. Life held on. Barely. In scattered pockets of warmth in an ocean of ice and darkness. For tens of millions of years. And then, as it has done so many times in its history, the Earth rescued itself. Because even when the surface was completely frozen, the planet's interior was still active. Magma was still churning beneath the crust, pressure was still building. And volcanoes, sealed under ice though they were, did not stop erupting. The eruptions punched through the ice in places, sending columns of ash and gas into the frozen sky. And the most important gas they released was carbon dioxide. Under normal circumstances, carbon dioxide is removed from the atmosphere by rain, which dissolves it and carries it into the ocean, and by the chemical weathering of rocks. But with the entire surface covered in ice, there was no rain. There was no exposed rock. There was no ocean surface to absorb the gas. The normal carbon cycle was completely shut down. So the carbon dioxide just accumulated. Every eruption added more. Every century, every millennium, the concentration climbed higher. For millions of years, volcanoes pumped carbon dioxide into an atmosphere that had no way to remove it. The greenhouse effect built and built and built, slowly at first, then faster, until the trapped heat began to overwhelm the reflective power of the ice. I want to stay with this image for a moment, because the snowball Earth is one of those events that is almost impossible to visualize accurately, and getting the scale right matters. Imagine standing at the equator during the snowball. Today, the equator is the warmest part of the planet, home to tropical rainforests and coral reefs, and water temperatures that rarely drop below 77 degrees Fahrenheit. During the snowball, the equator was covered in ice. Not a thin seasonal dusting, but a permanent sheet of glacial ice half a mile thick or more. The same kind of ice that today covers the interior of Antarctica. The entire planet looked the way Antarctica looks now, except there was no open water anywhere.
No liquid ocean surface, no rain, no rivers, no waves. The silence must have been extraordinary. On the modern Earth, the ocean is a constant source of sound. Waves, wind, marine life, the groaning of ice. During the snowball, there were no waves because there was no open water. There was no marine life large enough to make sound. There was only the wind screaming across a featureless plain of ice, and the occasional deep crack and rumble as the ice shifted and fractured under its own immense weight. And yet, hidden away, life persisted. The hydrothermal vents continued to operate because they are powered by the Earth's internal heat, not by sunlight. These vents were now beneath a ceiling of ice, pumping their mineral-rich water into sealed, dark cavities where tiny communities of bacteria clung to survival. Some scientists believe there may also have been thin patches of ice near the equator. Ice thin enough for a small amount of light to penetrate, allowing photosynthetic organisms to maintain a minimal existence. The snowball Earth was not a single event, but possibly a series of glaciation-deglaciation cycles. The planet froze, volcanic carbon dioxide accumulated, the ice melted, the climate overheated, weathering pulled the carbon dioxide back out, and the planet froze again. Each cycle lasted millions of years. Each cycle imposed extreme stress on the surviving organisms, and each cycle, the survivors that emerged were slightly different, slightly more resilient, slightly better equipped than the ones that had entered. The evolutionary biologist Andrew Knoll, whose work forms part of the foundation for the story we are telling tonight, has described the aftermath of the Snowball Earth episodes as a time of profound biological innovation.
The combination of extreme selective pressure during the glaciations and the flush of nutrients that followed the melting created a kind of evolutionary pressure cooker. Organisms that survived were tested to their absolute limits, and the adaptations they developed under that pressure became the raw material for the explosion of complexity that followed. The thaw, when it finally came, was catastrophic in its own way. It was not a gentle warming. The ice did not retreat slowly and gracefully over thousands of years. Once the greenhouse effect reached a critical intensity, the ice melted rapidly, geologically speaking. Perhaps over just a few thousand years, the planet went from completely frozen to scorching hot, with surface temperatures spiking far above modern levels, because the atmosphere was now saturated with carbon dioxide. Torrential rains fell onto newly exposed rock.
The chemical weathering of those rocks gradually pulled the excess carbon dioxide back out of the atmosphere, and over hundreds of thousands of years, the climate stabilized. But the world that emerged from the ice was profoundly different from the world that had entered it. And this is where the poison becomes the medicine. During the long freeze, the grinding of ice against rock had pulverized enormous quantities of minerals. When the ice melted, those minerals flooded into the oceans, creating a nutrient-rich soup. Phosphorus, iron, manganese, all the elements that living things need to build their molecular machinery were suddenly available in concentrations far higher than before. At the same time, the organisms that had survived the snowball were not the same organisms that had entered it. Tens of millions of years of extreme environmental stress had applied ferocious selective pressure. The survivors were tougher, more adaptable, more biochemically versatile. And among those survivors, the eukaryotic cells, the ones with mitochondrial power plants, were uniquely positioned to take advantage of the new, oxygen-rich, nutrient-rich oceans. Before the snowball, Eukaryotes had been a minor presence in a world still dominated by bacteria. After the snowball, they began to diversify rapidly. Some lineages developed the ability to photosynthesize by engulfing cyanobacteria, just as their ancestors had engulfed the bacteria that became mitochondria. These captured cyanobacteria became chloroplasts, giving eukaryotic cells the ability to harvest sunlight directly. The ancestors of all algae and all land plants trace back to this second great act of endosymbiosis. Other eukaryotic lineages went in a different direction. Instead of capturing light, they captured other cells. They became predators. And here, in the nutrient-rich waters of the post-snowball world, a new possibility began to emerge. Individual cells began to stick together, not just randomly, not just as temporary clumps, but in organized groups where different cells performed different functions. Some cells would handle digestion, others would handle movement, others would form a protective outer layer, multicellularity. The ability to build a body made of many cooperating cells, each specialized for a particular task. It is one of those innovations that sounds almost inevitable in hindsight, but was in fact extraordinarily unlikely. For over 2 billion years, life had been exclusively single-celled. Every organism was a complete, self-contained unit. The idea that individual cells would surrender their independence, give up their ability to reproduce freely, and instead become specialized components of a larger structure is almost paradoxical from an evolutionary perspective. Why would a cell sacrifice its own reproductive potential to serve a collective? The answer, most biologists believe, lies in the advantages of size and specialization. A multicellular organism can be larger than any single cell. It can move more effectively. It can exploit food sources that are inaccessible to individual cells. And when cells specialize, dividing labor among themselves, the whole organism can perform tasks that no single cell could manage alone. The trade-off, individual sacrifice for collective power, turned out to be one of the most successful strategies in the history of life. By roughly 635 million years ago, in the warm, nutrient-rich oceans that followed the last snowball, the first multicellular organisms began to appear in the fossil record. Welcome to the Ediacaran period. If you could dive into those ancient seas, you would encounter a world unlike anything that exists today. The seafloor was covered in soft, strange, quilted-looking organisms. Some resembled giant fern fronds anchored in the mud. Others looked like flattened discs or ribbed cushions, or segmented bags lying motionless on the sandy bottom. They had no heads, no tails, no limbs, no eyes, no mouths. Most of them appear to have absorbed nutrients directly through their skin, passively soaking up dissolved organic matter from the surrounding water. The Ediacaran garden was a place of absolute peace. There were no predators, there was no prey. Nothing chased anything, nothing ate anything. The organisms simply existed, side by side, growing and absorbing and quietly persisting in the dim underwater light. It was a world before violence. A world where multicellular life was experimenting with body plans, with the basic engineering challenges of being large, with the question of how to organize cells into something coherent. And for about 90 million years, this strange, peaceful experiment continued undisturbed. Let me take a moment with this Ediacaran world, because I think it deserves more than a quick summary. The creatures of the Ediacaran are among the strangest organisms that have ever lived, and the world they inhabited was unlike anything that exists today. The most famous Ediacaran fossil is Dickinsonia, an oval, ribbed organism that could grow to over 3 feet in length. It lay flat on the seafloor, a soft, quilted disc with no obvious front or back, no head, no tail, no limbs, no internal organs that we can identify from its fossils. For decades, scientists debated whether Dickinsonia was an animal, a fungus, a colonial organism, or something else entirely. Recent chemical analysis of exceptionally preserved specimens has found traces of cholesterol, a molecule that is characteristic of animal cell membranes, strongly suggesting that Dickinsonia was, in fact, an animal. But it was an animal unlike any that exists today. There was Charnia, a frond-like organism that could reach over 6 feet in length, anchored to the sea floor by a holdfast and extending upward into the water column like a giant feather. Charnia lived in deep water, well below the reach of sunlight, so it could not have been photosynthetic. It may have absorbed dissolved organic molecules directly through its surface, or it may have filter-fed on bacteria. Nobody is entirely sure. There were the rangeomorphs, branching fractal organisms that grew in patterns of self-similar repetition, each branch subdividing into smaller branches that subdivided into still smaller branches, creating a surface area so large relative to their volume that they could have absorbed nutrients with extraordinary efficiency. The Ediacaran seafloor, where these organisms lived, was covered in something called a microbial mat, a dense carpet of bacteria and other microorganisms that bound the sediment together into a tough, rubbery surface. Modern ocean floors are churned and disrupted by burrowing animals, worms and crabs and sea cucumbers that constantly rework the sediment. But in the Ediacaran, there were no burrowing animals. The microbial mats were intact, undisturbed, and the Ediacaran organisms lived on top of them, apparently grazing on the microbes or simply absorbing nutrients through their exposed surfaces. It was a world of surfaces, a flat, two-dimensional world where the primary challenge was not escaping predators or chasing prey, but maximizing contact with the nutrient-rich microbial mat. The body plans of Ediacaran organisms reflect this: flat, thin, spread out to maximize surface area. There was no advantage to speed, to armor, to aggression. The selective pressures were entirely different from anything that would follow. And here is what I find quietly moving about the Ediacaran. For roughly 90 million years, this was the state of multicellular life on Earth. Soft, passive, peaceful, strange. Life had made the leap from single cells to complex multicellular bodies, and instead of immediately becoming violent and competitive, it spent 90 million years in a kind of gentle experimentation, trying out body plans, testing the engineering of multicellularity, living in a world without fear. It could have gone on like that indefinitely. There was no law of nature that said peace had to end, no inevitable trajectory toward violence and predation. The Ediacaran garden persisted for almost as long as the entire age of dinosaurs would later last. It was a stable, successful, long-lasting experiment in a different way of being alive. But then, in one lineage, somewhere in the late Ediacaran oceans, a mutation occurred that produced something new: a body cavity, a digestive tract, a way to internalize food, to bring other organisms inside your body and break them down chemically, extracting their energy and nutrients with far greater efficiency than passive absorption could ever achieve. The first predator had arrived, and the garden was about to burn. But peace, on this planet, never lasts. Somewhere in the late Ediacaran, roughly 540 million years ago, evolution produced something that had never existed before: a mouth, a digestive cavity, a body plan designed not to absorb nutrients passively from the water, but to actively seek out, capture, and consume other organisms. Predation had been invented, and it would tear the Ediacaran garden apart. Because once one organism could eat another, the rules changed completely. Suddenly,
Being soft and immobile was a death sentence. Suddenly, there was an overwhelming evolutionary pressure to develop defenses, to grow hard shells, to develop the ability to move quickly, to see threats coming.
And there was an equally powerful pressure on the predators to become faster, stronger, more efficient at finding and capturing prey. An arms race. The most consequential arms race in the history of life, and it was about to explode with a fury that the world had never seen. 3 times now the pattern has held: collision, oxygen, ice. Each one should have ended the story. Each one wrote the next chapter instead. And if you are still awake, you might be starting to wonder, is this a coincidence, or is it a rule? Does life need catastrophe, the way a fire needs oxygen? We are not done testing the hypothesis, because the next poison will not come from the planet or the atmosphere. It will come from life itself. The invention of hunger, of predation, of one creature devouring another, is a poison of a very different kind. Not a chemical poison like oxygen, not a physical poison like ice. A biological poison, the end of innocence.
And, like every poison before it, it would turn out to be the greatest medicine of all. Chapter 4. The fourth poison. Hunger. There is something almost poignant about the Ediacaran world, that last garden of peace before everything changed. For 90 million years, multicellular life existed in a state that we might almost call innocent. Soft creatures on a quiet seafloor, absorbing their food from the water, bothering no one. No teeth, no claws, no fear. And then the mouth appeared, and the meaning of life on Earth changed forever. I want to be precise about what happened next, because the speed of it is genuinely shocking. The transition from the quiet Ediacaran to the violent, explosive, wildly creative Cambrian period is one of the most dramatic events in the entire fossil record. Paleontologists call it the Cambrian explosion, and the word explosion is not an overstatement.
Starting roughly 540 million years ago and accelerating over the next 20 to 25 million years, essentially every major animal body plan that exists today appeared in the fossil record. Creatures with hard shells, creatures with jointed legs, creatures with segmented bodies, creatures with internal skeletons. Worms, arthropods, mollusks, the ancestors of starfish and sea urchins, the earliest chordates, the lineage that would eventually lead to fish, to amphibians, to reptiles, to mammals, to you. All of these fundamental designs, all of these blueprints for building animal bodies emerged within a geological blink of an eye. Why so fast? What caused this sudden burst of evolutionary creativity after billions of years of mostly single-celled life? The answer most evolutionary biologists now believe is predation.
The invention of eating other organisms created an evolutionary pressure so intense, so relentless, so inescapable, that it forced life into a desperate sprint of innovation. Before predation, there was no particular advantage to being fast, or armored, or perceptive. You could sit on the sea floor and absorb nutrients and survive just fine. After predation, every organism was locked into a survival contest. If you could not outrun, outfight, or outsmart the thing that was trying to eat you, you died. And your genes died with you. Consider what that pressure produced. Organisms began extracting calcium carbonate from seawater and using it to build hard external shells. Armor. For the first time,
The bodies of living things included mineral components, hard structures that could resist the crushing force of a predator's grasp. Trilobites, those iconic creatures of the Cambrian seas, developed some of the most sophisticated armor in the animal kingdom, with their bodies encased in jointed, flexible shells of calcite that allowed them to curl into defensive balls when threatened. Other organisms responded by developing spines, sharp projections that made them unpleasant to eat. Others grew larger, because size itself is a defense. Others developed the ability to burrow into the sediment, hiding from predators in the safety of the mud. But the single most revolutionary innovation of the Cambrian was not a weapon or a piece of armor. It was a sense organ, the eye. Before the Cambrian, the world was blind. Every organism experienced its environment through chemical gradients, through touch, through vibrations in the water. But no organism could see. There were no eyes, no light-sensitive organs of any kind. The ocean was, in a visual sense, a world of complete darkness, even in the sunlit shallows. And then, over a geologically brief period, photoreceptor cells began to cluster and organize. Simple, light-sensitive patches evolved into pit-shaped structures that could detect the direction of light. Those pits deepened and narrowed, forming crude pinhole cameras that could form rough images. Lenses appeared, transparent mineral structures that focused light onto dense arrays of photoreceptor cells. And suddenly, for the first time in 4 billion years, an organism could see. The consequences were immediate and devastating. A predator that could see its prey from a distance had an enormous advantage over one that had to stumble into its food by accident. A prey animal that could see a predator approaching had a chance to flee before contact was made. Vision transformed the ocean from a world of chance encounters into a world of calculated pursuit and evasion. The arms race accelerated by an order of magnitude. And I want to make sure the full strangeness of the Cambrian explosion registers, because it is easy to read about it as a list of innovations, shells, eyes, legs, and miss the sheer weirdness of what was happening. The Cambrian seas were full of creatures that looked like nothing alive today. Opabinia, with its 5 eyes and a long, flexible vacuum cleaner-like proboscis extending from the front of its head. Hallucigenia, which was so bizarre that scientists initially reconstructed it upside down, mistaking its legs for spines and its spines for legs. Wiwaxia, covered in overlapping scales and long spines, looking like something between a sea slug and a medieval mace. The Cambrian was not just an explosion of diversity, it was an explosion of experimentation. Evolution was trying out body plans that had never been tested before and would never be tried again. The famous Burgess Shale fossil deposit in British Columbia, discovered by Charles Walcott in 1909 and reinterpreted by Harry Whittington, Derek Briggs, and Simon Conway Morris in the 1970s and 1980s, preserves an extraordinary snapshot of this experimental period. The soft-bodied preservation at Burgess gives us creatures with intact internal organs, eyes, guts, and appendages that would normally decay and vanish from the fossil record. Looking at the Burgess Shale fauna is like opening a window into a world that evolution was still assembling, testing prototype after prototype, discarding most of them, and keeping only the few designs that worked well enough to persist. Most of the Cambrian's experimental body plans did go extinct. The wild proliferation of forms was gradually pruned by natural selection into the more familiar set of animal groups that we recognize today. But the basic architectural templates, the fundamental body plans, the phyla, were established during this brief period and have persisted ever since. Every animal alive today belongs to a phylum that originated in or shortly after the Cambrian explosion. And the creature that best exemplified this new world of visual predation was Anomalocaris, the first apex predator in the history of life. Picture it, a segmented body up to 3 feet long, an extraordinary size in an ocean where most organisms were still measured in millimeters. Two large, stalked compound eyes, each containing thousands of individual lenses, giving it a panoramic view of its surroundings. A pair of large, spiny, grasping appendages at the front of its head, curving inward like the tongs of a grabbing crane. And a circular mouth lined with hard, tooth-like plates that could contract like a camera iris, crushing the shells of trilobites and feeding the fragments inward. Anomalocaris was the Tyrannosaurus rex of the Cambrian seas, the first true predator king, and its existence forced every other organism in the ocean to evolve faster, build better defenses, develop sharper senses, or die. The poison of hunger, the violent end of the peaceful Ediacaran garden, had become the most powerful creative engine in the history of life. More new body plans appeared in the 25 million years of the Cambrian explosion than in the entire 3.5 billion years that preceded it. The arms race between predator and prey, the relentless pressure to eat or be eaten, drove innovation at a rate that makes all other evolutionary periods look glacial by comparison. And the innovations kept coming. Over the next 300 million years, from the Cambrian through the Ordovician, Silurian, Devonian, and Carboniferous periods, life continued to diversify, to grow more complex, to explore new environments. Fish appeared, the first vertebrates, animals with internal skeletons of bone or cartilage. The internal skeleton was a profound innovation because it allowed organisms to grow large while maintaining structural integrity. An external shell can only be so big before it becomes too heavy to move. An internal skeleton can scale up much further, supporting larger bodies, stronger muscles, faster movement. The oceans filled with fish of every description, from small, jawless filter feeders to massive armored predators like Dunkleosteus, a fish the size of a small bus, with jaws that could deliver one of the most powerful bites of any animal in history, despite having no teeth. Its jaws were lined with sharp, bony plates that self-sharpened as they slid past each other, like scissors being honed with every cut. Meanwhile, on land, something equally momentous was happening. For the first 4 billion years of Earth's history, the continents had been barren rock.
No soil, no plants, no animals. The land was a lifeless desert bombarded by ultraviolet radiation, because the ozone layer, which depends on atmospheric oxygen, had only recently become thick enough to provide meaningful protection. But by the Silurian period, roughly 430 million years ago, the ozone shield was in place, and life began, cautiously, tentatively, to leave the water. Plants came first, or rather, the ancestors of plants, which were green algae that had been living in shallow freshwater environments. These organisms faced enormous challenges on land. They needed to resist drying out. They needed structural support against gravity, which is far more demanding on land than in the buoyancy of water. They needed to transport water and nutrients through their bodies without the surrounding medium of water to carry things along. The solutions they found were elegant: waxy coatings on their surfaces to prevent water loss. Rigid cell walls reinforced with cellulose and later lignin, the tough structural polymer that gives wood its strength. Root systems that anchored them in the ground and absorbed water and minerals from the soil. Vascular systems, networks of tiny tubes that carried water upward from the roots and sugars downward from the leaves. The colonization of land by plants transformed the continental surfaces. For the first time, the bare rock was broken down by root acids and bound together by organic matter, creating soil. Where there had been only stone, there was now a living skin of earth. And where there was soil and vegetation, there was food. And where there was food, animals followed. Arthropods were the first animals on land, the ancestors of insects, spiders, scorpions, and centipedes. They brought with them the chitinous exoskeletons that had served them well in the sea, which, conveniently, also helped prevent water loss on land.
They developed new respiratory systems, tracheal tubes that carried air directly to their tissues, replacing the gills that had served them in the water. And then, roughly 375 million years ago, our own ancestors made the crossing. Lobe-finned fish, creatures like Tiktaalik, used their muscular, limb-like fins to haul themselves through shallow swamps and across mudflats. Over millions of years, those fins became legs, those gill chambers became lungs, and the first tetrapods, four-limbed vertebrates, crawled up onto the land and stayed. And I want to pause here on Tiktaalik, because this creature holds a special place in the story, and the circumstances of its discovery are genuinely remarkable. In 2004, a team of paleontologists led by Neil Shubin set out to find a fossil that would illuminate the transition from fish to land-dwelling tetrapods.
They knew from existing fossils roughly when this transition had occurred, around 375 million years ago. And they knew that the rocks of Ellesmere Island in the Canadian Arctic were the right age and the right type. Ancient river deposits from a tropical region that was at the equator during the Devonian period, long before continental drift carried it to its current frigid location. After several years of searching in some of the most remote and inhospitable terrain on Earth, they found what they were looking for. A fossil that was almost perfectly half fish and half tetrapod. It had the scales and fins of a fish, but those fins contained the bones of a wrist and primitive fingers. It had a flat, crocodile-like head that could move independently of its shoulders, something no fish can do, but every land animal can. It had both gills and rudimentary lungs. Tiktaalik was not yet a land animal.
It was almost certainly an aquatic creature that lived in shallow, swampy environments. But it could do something that no ordinary fish could do. It could prop itself up on its muscular, limb-like fins and push its head above the water surface. It could breathe air. It could look around at the world above the waterline. It was a fish that was beginning to walk. Why would a fish want to leave the water? What possible advantage could there be in crawling out onto land? The answer, most biologists believe, lies in the ecology of Devonian swamps. These were warm, shallow, plant-choked waterways with low oxygen levels. The water was so dense with vegetation and decaying organic matter that dissolved oxygen was scarce. Fish that could gulp air at the surface, supplementing their gill-based respiration with primitive lungs, had a survival advantage. And fish that could haul themselves over mudflats from one drying pool to another could access food sources and habitats that fully aquatic fish could not reach. The journey from water to land was not a single dramatic event. It was a gradual process, spanning tens of millions of years, in which a lineage of fish slowly adapted to spending more and more time out of water. Each generation was slightly better at the challenges of terrestrial life than the last. Fins became limbs. Gills gave way to lungs. Scales were gradually replaced by skin that could resist drying out. And with each step, these early tetrapods gained access to a world of resources that had been accumulating for hundreds of millions of years. By the time the first vertebrates crawled onto land, plants had already been there for at least
50 million years, building soil, creating habitats, and producing an abundance of organic matter.
Insects and other arthropods had already colonized the land, providing a rich food source for any vertebrate that could catch them. The land was not an empty wasteland. It was a feast waiting for someone with the right equipment to exploit it. And exploit it they did. From those first tentative crawls through Devonian mudflats, the tetrapods diversified into amphibians, then into reptiles, and ultimately into every land vertebrate that has ever existed. Every frog, every lizard, every bird, every mammal, every human being is a direct descendant of a fish that learned to walk. The Carboniferous period, from about 359 to 299 million years ago, was the result of all this innovation. And it was extraordinary. Dense, humid, tropical swamp forests covered vast areas of the continents. The trees were not like modern trees. They were giant lycopsids, scaled trees with trunks covered in diamond-shaped leaf scars, towering 100 feet or more into a canopy so thick that the forest floor was in perpetual twilight. And the atmosphere during the Carboniferous was different from today in one crucial respect. Oxygen levels were astonishingly high, around 35% of the atmosphere compared to 21% today. The reason was a quirk of biology. The trees of the Carboniferous were rich in lignin, but the bacteria and fungi that decompose wood had not yet fully evolved the enzymes needed to break lignin down. When these giant trees fell, they did not rot. They simply piled up, layer upon layer, eventually being buried under sediment and compressed into coal. All that carbon, locked away underground, meant that the carbon dioxide it had originally been made from stayed out of the atmosphere, and the oxygen that photosynthesis had released stayed in.
The high oxygen levels had dramatic effects on animal life, particularly on insects and other arthropods, which breathe through a system of tiny tubes called tracheae. In higher oxygen concentrations, these tubes can support gas exchange in much larger bodies. The result was a world of giant insects. Meganeura, a dragonfly relative with a wingspan approaching 2.5 feet. Arthropleura, a millipede-like creature over 6 feet long. The Carboniferous forests were a world where the underbrush rustled with creatures of a size that would be nightmarish by modern standards. Those Carboniferous forests are worth dwelling on for another reason. The coal that formed from their buried remains would sit underground for 300 million years, a vast reservoir of ancient carbon, locked away, inert, doing nothing. And then, in the 18th century, humans figured out how to dig it up and burn it.
The coal that powers industrial civilization, the coal that drove the steam engines and the locomotives and the factories that transformed human society, is literally the compressed remains of Carboniferous trees. When you burn coal, you are releasing carbon that was captured from the atmosphere by photosynthesis 300 million years ago. Carbon that was locked away precisely because nothing in the Carboniferous could decompose those trees. The carbon cycle connects everything in this story. Carbon moves from the atmosphere into living organisms through photosynthesis, from living organisms into the soil and sediments when they die, from sediments into rock over geological time, and back into the atmosphere through volcanic eruptions, and, more recently, through the burning of fossil fuels. The current rise in atmospheric carbon dioxide is, in a very literal sense, the reversal of a process that began in the Carboniferous. We are putting back into the atmosphere carbon that ancient trees removed hundreds of millions of years ago. We are undoing, in centuries, what took tens of millions of years to accomplish. The Carboniferous also gave us something else: the first reptiles. While the giant insects and amphibians dominated the swampy lowlands, a new group of vertebrates was quietly evolving in the drier upland environments. Reptiles had developed a crucial innovation, the amniotic egg. Unlike amphibians, which had to return to water to lay their eggs, reptiles produced eggs with a tough, waterproof shell and internal membranes that supplied the developing embryo with everything it needed. For the first time, vertebrates could reproduce entirely on land, free from any dependence on water. This liberation from water opened up the drier continental interiors, environments that amphibians could not access. Reptiles diversified rapidly, and among their descendants would eventually be the dinosaurs, the birds, and, on a separate branch, the mammals. The amniotic egg, that quiet innovation of the Carboniferous uplands, was the key that unlocked the rest of vertebrate history. Life had conquered the oceans, the freshwater systems, and the land. It had developed hard shells, internal skeletons, legs, lungs, eyes, wings. The biosphere was rich, diverse, complex, interconnected. Food webs of extraordinary intricacy linked predators and prey in networks that spanned entire continents. It had taken nearly 4 billion years to get here, from that first fragile cell at a hydrothermal vent to a planet teeming with giant forests and armored fish and flying insects. The poisons of collision, oxygen, and ice had each nearly ended the story, and each had instead opened the door to something grander. But the planet was not done. The greatest test was yet to come, and it would arrive from below. Deep beneath the surface of what is now Siberia, a system of cracks in the Earth's crust was slowly widening, fed by a rising plume of impossibly hot magma from deep in the mantle. The largest volcanic event in Earth's history was building pressure. And when it finally erupted, it would come closer to ending life on Earth than anything before or since. 4 poisons, 4 medicines. Each time the destruction was more extreme, and each time the recovery produced something more complex than what had been destroyed. You might start to think the pattern is reliable, that no matter what happens, life will bounce back stronger than before. The next chapter will test that belief to its absolute limit, because the 5th poison nearly broke the pattern entirely. The 5th poison was fire, and it was about to burn the world. Chapter 5. The 5th poison, fire from below. 252 million years ago, the Earth looked very different from today. All of the major land masses had drifted together over hundreds of millions of years, colliding and fusing into a single supercontinent that geologists call Pangaea, from the Greek for all lands. Pangaea stretched nearly from pole to pole, a vast, unbroken expanse of land surrounded by a single global ocean called Panthalassa. The interior of Pangaea was harsh. Far from the moderating influence of the ocean, the central regions experienced extreme temperatures, scorching summers and brutal winters, with vast deserts where rain almost never fell. The coastlines were more hospitable, fringed with forests and wetlands, where the ancestors of modern reptiles basked and hunted. The oceans were warm, home to diverse communities of fish, corals, brachiopods, crinoids, and the last great populations of trilobites, those armored arthropods that had been a fixture of the seas since the Cambrian. Life was thriving. 300 million years of post-Cambrian evolution had built a biosphere of staggering complexity. Food webs on land and in the sea were densely interconnected. Ecosystems hummed with the activity of millions of species, filling every conceivable niche. And then, beneath the eastern edge of Pangaea, in the region that would one day become Siberia, the Earth opened up. The Siberian traps, as geologists now call them,
were not a single volcanic eruption. They were a sustained, apocalyptic outpouring of lava and gas that lasted for roughly 1 million years. The scale is almost impossible to comprehend. The total volume of lava that poured out of the Earth during this event was enough to bury the entire continental United States under more than 1/2 mile of molten rock. A flood of basalt that covered millions of square miles, burying everything in its path. But the lava, terrible as it was not the main killer.
Lava flows are devastating locally, but they cannot, by themselves, cause a global extinction. What made the Siberian traps lethal on a planetary scale was what happened when all that rising magma encountered something on its way to the surface: coal. Beneath the Siberian crust lay enormous deposits of coal and other carbon-rich sedimentary rocks, the buried remains of ancient forests, possibly including some from the Carboniferous period. When the superheated magma intruded into these coal deposits, it cooked them. Trillions of tons of carbon dioxide and methane were liberated from the rock and blasted into the atmosphere. The effect was a runaway greenhouse crisis that dwarfed anything Earth had experienced since the Hadean. Global temperatures spiked. The oceans warmed dramatically, with surface temperatures in tropical regions possibly reaching 104 degrees Fahrenheit or higher, far above the thermal tolerance of most marine organisms.
The warmer water held less dissolved oxygen, suffocating creatures that depended on it. In the deepest parts of the ocean, where oxygen was already scarce, conditions became completely oxygen-starved, lifeless, dead zones that expanded relentlessly. And in those suffocating, oxygen-starved waters, a particular type of bacteria thrived. Anaerobic, sulfur-reducing bacteria, organisms that had been lurking in oxygen-poor niches since the earliest days of life, now found their habitat expanding globally. Their metabolic waste product was hydrogen sulfide, a gas that is toxic to almost all aerobic life. As these bacteria bloomed in the warming, deoxygenated oceans, they pumped massive quantities of hydrogen sulfide into the water and, eventually, into the atmosphere itself. Hydrogen sulfide in the atmosphere would have done two things. First, it would have poisoned land-dwelling animals directly, since the gas is lethal at even modest concentrations. Second, it would have attacked and degraded the ozone layer, stripping away the ultraviolet shield that had protected life on land for hundreds of millions of years. With the ozone weakened or destroyed, intense ultraviolet radiation would have hammered the surface, damaging the DNA of any organism exposed to sunlight. The killing was comprehensive and relentless. In the oceans, 96% of all marine species went extinct. On land, approximately 70% of terrestrial vertebrate species disappeared. The trilobites, which had survived every previous crisis for over 300 million years, were finally erased completely. The great forests were devastated. Insect diversity collapsed. The intricate food webs that had taken hundreds of millions of years to build were shredded in a geological instant. The Permian extinction, the Great Dying, was the closest life on Earth has ever come to total annihilation. And it was caused not by a single event, but by a cascade, a chain reaction where each consequence triggered the next. Volcanism released carbon. Carbon warmed the climate. Warming deoxygenated the oceans. Deoxygenation allowed sulfur bacteria to bloom. Sulfur bacteria poisoned the atmosphere and destroyed the ozone. Each link in the chain made the next link worse. A perfect storm of compounding disasters. And here is the development that should stop you cold. The margin of survival was terrifyingly thin. 96% of marine species gone. That means 4% survived. 4%. If the eruptions had lasted a little longer, if the coal deposits beneath Siberia had been a little richer, if the ocean circulation had been a little weaker, if any one of a dozen factors had been slightly different, that 4% might have been 0. And if it had been 0, there would be no fish in the sea today, no amphibians, no reptiles, no birds, no mammals, no you.
The entire subsequent history of complex life on Earth depends on the fact that the Permian extinction stopped just short of complete. 4% of marine species held on through a hell of heat, poison, and radiation. And from that tiny remnant, the entire modern biosphere was rebuilt. Think about that tonight. 4%. Every whale, every eagle, every dog, every human being alive today is descended from organisms that survived the worst catastrophe in the history of life. You are here because 4% held on. The recovery was slow. For millions of years after the eruptions ceased and the atmosphere began to stabilize, Earth was a bleak and empty world. The oceans were largely lifeless. The land was barren. The ecosystems that had taken hundreds of millions of years to build were gone, and there was no shortcut to rebuilding them. Evolution had to start nearly from scratch, filling empty niches with new species, building new food webs, establishing new ecological relationships. But the emptiness itself was a gift. This is the paradox that runs through every chapter of this story. The devastation of the Permian extinction created an opportunity that would not have existed otherwise. With the old dominant species gone, the survivors found themselves in a world without competition. Ecological niches that had been occupied for hundreds of millions of years were suddenly vacant. And among the survivors, one group was particularly well positioned to take advantage. The Permian extinction was not a sudden event, despite how it may sound in summary. The killing unfolded over roughly 60,000 years, perhaps longer. That may seem fast in geological terms, and it is, but it means that individual organisms did not experience a single moment of catastrophe. They experienced a slowly worsening world. Each generation lived in conditions slightly more hostile than the one before. The oceans grew slightly warmer, slightly more oxygen depleted, slightly more toxic. The air became slightly more difficult to breathe. Food became slightly scarcer. The last trilobites, those armored arthropods that had been fixtures of the ocean floor for over 300 million years, surviving the Ordovician mass extinction, the late Devonian extinction, and every other crisis that had come before, finally succumbed. They had been declining for millions of years before the Permian event, their diversity slowly shrinking. The Siberian traps finished them off. After 300 million years of continuous existence, longer than any other complex animal group in the fossil record, the trilobites vanished forever. On land, the dominant large animals of the Permian, the synapsids, which were the group that included our own distant ancestors, were devastated.
The largest synapsids, the Gorgonopsians, apex predators with saber-like teeth, went extinct completely. Only the smallest, most generalized synapsids survived. The tiny therapsids that had lived on the margins of the Permian world, eating insects and hiding from larger animals. These survivors are worth paying attention to, because the survivors of mass extinctions are always worth paying attention to. They are never the dominant species of the preceding era. They are never the apex predators, the largest herbivores, the most specialized organisms. The survivors are always the generalists, the small ones, the ones that needed the least and could tolerate the most. This is the pattern that repeats at every mass extinction in Earth's history, and it carries a lesson that may be relevant to our own future. The recovery from the Permian took longer than any other post-extinction recovery in the geological record.
Perhaps 10 million years passed before ecosystems reached anything approaching their former complexity. The early Triassic, the period immediately following the extinction, was a strange and impoverished time. Fossil assemblages from this period show very low diversity, with a few generalist species dominating across enormous geographic ranges. The normal pattern of ecological specialization, where different species fill different niches in different environments, had collapsed into a kind of ecological monotony. But slowly, generation by generation, diversity rebuilt. New species appeared, new niches were filled, new food webs formed. And among the organisms that were diversifying most rapidly in this new, post-apocalyptic world were the archosaurs. They were small, unassuming reptiles. A group called the archosaurs, the ruling reptiles. During the Permian, they had been minor players, overshadowed by larger, more established lineages. But they had survived the extinction. And in the empty, post-apocalyptic world, they diversified rapidly. Some lineages developed the ability to walk upright on two legs, freeing their forelimbs for other uses. Their metabolisms became more active, more energetic. Their body plans became more varied. And from one branch of the archosaurs, roughly 240 million years ago, a new kind of creature emerged: the dinosaurs. Their rise was not immediate or inevitable. For the first 30 million years or so, dinosaurs were just one of several groups of archosaurs competing for dominance. But they possessed certain advantages: efficient locomotion, active metabolisms, and body plans that could scale from small and nimble to large and powerful. And when another, smaller extinction event, around 201 million years ago, knocked out many of their remaining competitors, the dinosaurs stepped into the void and never looked back. For the next 160 million years, give or take, dinosaurs were the undisputed rulers of the land. And their reign was not a monotonous stretch of sameness. The dinosaurs diversified into an extraordinary range of forms, filling every major ecological niche on every continent. The sauropods, the long-necked herbivores, were the largest land animals that have ever existed. Argentinosaurus may have weighed nearly 100 tons, with a body length of over 100 feet. Their necks, some stretching 50 feet or more, allowed them to feed on treetops that no other herbivore could reach. When a herd of sauropods moved across a floodplain, the ground shook. They literally reshaped landscapes, their massive bodies flattening vegetation and compacting soil in their wake. The theropods, the bipedal predators, included everything from chicken-sized hunters to the apex predators that have become the most famous animals in the history of paleontology.
And the most famous of all, of course, was Tyrannosaurus rex. There is a reason T-Rex captures the imagination in a way that almost no other extinct animal does. It was a near-perfect killing machine. 40 feet long, standing 15 feet tall at the hip, weighing 8 or 9 tons. Its skull alone was over 5 feet long, filled with teeth the size of bananas, thick and serrated, and backed by jaw muscles that could generate a bite force of roughly 12,000 pounds, enough to crush solid bone. T-Rex did not just kill its prey, it pulverized it. The fossilized droppings of T-Rex contain fragments of shattered bone, evidence that it consumed not just the flesh, but the skeletal structure of its victims. For about 2 million years, T-Rex sat at the absolute peak of the food chain, the supreme predator of the late Cretaceous. It had no natural enemies, no competitor that could challenge it. It looked down on the world from the top, as though that position were permanent. But nothing on this planet is permanent, and the next poison was already on its way. It was not rising from below, like the Siberian traps. It was falling from above. A rock, roughly 6 miles across, traveling at 43,000 miles per hour, aimed by pure cosmic chance at a shallow sea on the coast of what would one day be called Mexico. The 6th poison was approaching, and this one would arrive in an afternoon. Chapter 6. The 6th poison. Stone from the sky. 66 million years ago. A late afternoon somewhere in what is now North America. The Cretaceous world is at its peak. Flowering plants have transformed the landscape, producing fruits and seeds that support a new generation of insects, birds, and mammals. Vast forests of flowering trees cover the continents. The oceans are warm, teeming with marine reptiles, ammonites, and the enormous mosasaurs, aquatic predators that have replaced the earlier ichthyosaurs as the apex hunters of the deep. On land, herds of triceratops browse on low vegetation, their massive, frilled heads swinging slowly as they crop ferns and shrubs. Somewhere nearby, a Tyrannosaurus rex is moving through the undergrowth, following a scent trail, its 2-ton head swiveling on its thick neck, eyes scanning the tree line. It is a world of extraordinary richness and complexity. 160 million years of dinosaur evolution have produced an ecosystem so intricate, so densely interconnected, that it seems unshakable. The dinosaurs have survived ice ages and warm periods, continental drift and volcanic eruptions, the rise and fall of sea levels. They have adapted to every environment on Earth, from polar forests to tropical jungles. Their dominion seems absolute and eternal. And the dinosaur world was not just about the famous giants. The Mesozoic era saw innovations that would echo far into the future. Among the smaller theropod dinosaurs, a lineage began developing an insulating body covering. Feathers. The earliest feathers were not flight feathers. They were simple filaments, hair-like structures that probably served as insulation, helping smaller dinosaurs maintain a stable body temperature. Over millions of years, these simple structures became more complex, developing branching barbs and flat veins that could trap air and provide increasingly effective insulation. And then, in one lineage, the feathers became large enough and the arms long enough and the body light enough that a new possibility opened up. Flight. The dinosaurs that took to the air became birds. Not a separate group that replaced the dinosaurs, but a direct continuation of the dinosaur lineage, carrying dinosaur DNA and dinosaur skeletal architecture into a new realm. When you watch a sparrow hop across a garden fence, you are watching a dinosaur. A small, feathered, flying dinosaur. The last surviving branch of a family tree that once included Argentinosaurus and Tyrannosaurus rex. During the Mesozoic, the mammals were also present, but they were relegated to the margins. Small, nocturnal, insectivorous creatures, most no larger than a modern rat, scurrying through the underbrush
and hiding from dinosaur predators. For over 160 million years, mammals lived in the shadows. They could not compete with the dinosaurs for the large animal niches. They were suppressed, constrained, kept small and furtive by the overwhelming dominance of the ruling reptiles. But those long years in the shadows were not wasted. In the quiet margins of the dinosaur world, mammals were developing adaptations that would later prove decisive. Warm blood, the ability to maintain a constant internal body temperature regardless of external conditions. Fur, for insulation, a more efficient jaw structure that allowed for the complex chewing of food, extracting more nutrition from each meal. Larger brains relative to body size, supporting more sophisticated behavior. Live birth and extended parental care, with mothers nursing their young through the most vulnerable period of their lives. These adaptations made mammals excellent survivors in harsh conditions, but they could not overcome the sheer dominance of the dinosaurs in an intact ecosystem. The mammals needed something to change. They needed the slate to be wiped clean. They needed a catastrophe. They had no way of knowing it, but their catastrophe was already on its way. Somewhere in the asteroid belt between Mars and Jupiter, or perhaps in the outer reaches of the solar system, a rock, roughly 6 miles across, had been nudged out of its orbit by the gravitational influence of a passing body. It was falling inward, toward the Sun, on a trajectory that would intersect with the orbit of a small blue planet in the inner solar system. 5 times now, destruction has cleared the ground for something that could not have existed without it. 5 poisons, 5 medicines. But notice how the margins keep getting thinner. 96% dead, 4% alive. The pattern held, barely, by a thread so thin it could have snapped at any moment. And it was about to be tested one final time. The clock was ticking on the age of dinosaurs, and the mammals, patient and small and hidden, were about to inherit the Earth. And then a new star appears in the daytime sky. At first it would have looked like a bright point of light. Then, over the course of perhaps a few minutes, it would have grown. Brighter, larger, a streak of fire drawing a line across the blue sky. And then, very quickly, it would have filled a significant portion of the visual field. A blazing mass trailing a column of superheated gas and debris, growing larger with terrifying speed. The asteroid that ended the age of dinosaurs was roughly 6 miles across. A rock larger than Mount Everest, traveling at approximately 43,000 miles per hour, about 12 miles per second. At that velocity, the atmosphere was no barrier at all. The asteroid punched through the entire thickness of the atmosphere in less than 2 seconds, compressing the air ahead of it so violently that the air itself ignited into a sheath of plasma thousands of degrees hot. It struck the shallow waters of what is now the Gulf of Mexico, near the modern Yucatan Peninsula, in a spot that geologists now call Chicxulub. And the impact released energy equivalent to roughly 100 million megatons of TNT. To put that number in context, the entire global nuclear arsenal, every warhead ever built by every nation, totals approximately 10,000 megatons. The Chicxulub impact was 10,000 times that. In the first second, a fireball hotter than the surface of the sun expanded outward from the impact site. Every living thing within 600 miles was vaporized, not burned, not killed, literally converted to gas. The asteroid itself was destroyed, along with a massive volume of the Earth's crust. The impact punched a crater roughly 90 miles wide and 12 miles deep, excavating down through sedimentary rock, through the crust, and into the upper mantle beneath. The shockwave, an expanding wall of compressed air traveling at thousands of miles per hour, flattened forests across the continent. Earthquakes of magnitude 11 or greater, far beyond anything in recorded human history, rippled through the crust, triggering volcanic eruptions on the opposite side of the planet.
Tsunamis, hundreds of feet tall, radiated outward from the impact site, crossing the Gulf of Mexico and slamming into coastlines thousands of miles away, sweeping hundreds of miles inland, carrying everything before them. But the immediate destruction, as devastating as it was only the beginning. The impact ejected billions of tons of pulverized rock and vaporized minerals into the upper atmosphere and beyond, into space itself. This material, flung high above the atmosphere, cooled rapidly in the vacuum and fell back as a rain of glowing glass spherules, tiny molten droplets re-entering the atmosphere at high speed. The friction of re-entry heated these particles until they glowed white-hot, and as they rained down across the entire planet, they raised atmospheric temperatures to the point where forests spontaneously ignited. Wildfires swept across every continent. The entire surface of the Earth was, for a brief period, a furnace. And then came the darkness. The fires consumed billions of tons of vegetation, and the impact itself had vaporized massive quantities of sulfur-rich rock from the Yucatan seabed. The resulting clouds of soot, ash, and sulfur aerosols rose into the stratosphere and spread around the globe, forming an opaque veil that blocked sunlight almost completely. For months, perhaps for years, the Earth was plunged into near-total darkness. Photosynthesis ceased. The base of the food chain, the green plants and photosynthetic algae that ultimately supported every ecosystem on the planet, collapsed. Global temperatures, which had briefly spiked during the firestorm, now plummeted as the sunlight-blocking aerosols cooled the surface. The planet entered a prolonged impact winter, with temperatures dropping well below freezing across most of the globe. The combination of darkness, cold, and the failure of photosynthesis devastated every ecosystem on Earth simultaneously. The large dinosaurs died first. The herbivores starved as vegetation withered. The carnivores starved as the herbivores disappeared. Animals that had evolved over 160 million years, that had survived every previous challenge, that had been the most successful large animals in the history of the planet, perished in the dark and the cold, their bodies lying unburied on frozen ground. 75% of all species on Earth went extinct, all non-avian dinosaurs, every single species except the lineage that would become modern birds, vanished. The mosasaurs, the plesiosaurs, the pterosaurs, the ammonites, all gone. 160 million years of dominion erased in a geological instant. And here is where I want you to think about something that does not often make it into the popular accounts of the Chicxulub impact. The asteroid did not have to hit where it hit. A rock traveling through the solar system at 12 miles per second, arriving at a planet rotating on its axis at roughly 1,000 miles per hour at the equator, could have struck essentially anywhere on Earth's surface. The specific impact site was a matter of cosmic chance, the intersection of two trajectories in a universe that does not aim, and the specific impact site mattered enormously. The Yucatan Peninsula, 66 million years ago, was a shallow sea underlain by thick deposits of limestone and anhydrite, a mineral rich in sulfur. When the asteroid vaporized this rock, it released staggering quantities of sulfur into the atmosphere. Sulfur aerosols are exceptionally effective at blocking sunlight and cooling the climate. If the asteroid had struck deep ocean, which covers roughly 70% of the Earth's surface, the sulfur release would have been far lower. The impact winter would have been shorter, less severe.
Many scientists believe that in a deep ocean impact scenario, the dinosaurs might have survived. Think about what that means. The difference between the world you live in and a world still ruled by dinosaurs. A world where mammals remained small, nocturnal, and marginal. A world where no primate ever descended from a tree and no human being ever existed. That difference may come down to where, on a spinning globe, a randomly falling rock happened to land. The improbability is staggering. You exist because of a cosmic coin flip. Heads, the rock hits deep ocean, the dinosaurs survive, mammals stay small, and the entire trajectory of evolution follows a completely different path. Tails, the rock hits shallow, sulfur-rich water, the darkness lasts long enough to kill the dinosaurs, and the small, warm-blooded, fur-covered creatures in their underground burrows inherit the planet. The coin came up tails, and here you are.
Now let us talk about those small creatures, because they are your ancestors, and their survival story deserves to be told with the respect it warrants. When the asteroid struck, the mammals of the late Cretaceous were, by and large, small. Most were no bigger than a modern rat or shrew. They lived in burrows, in hollow logs, in crevices between rocks. Many were nocturnal, active at night when the dinosaurs that would have eaten them were less active. They ate insects, seeds, small invertebrates. They were generalists, adaptable, unspecialized. In the world of the dinosaurs, they were marginal, minor players in a drama dominated by giants. And those very qualities, the qualities that made them insignificant in the Cretaceous, turned out to be exactly what they needed to survive the catastrophe. The burrows provided shelter from the initial firestorm and the subsequent cold. The small body size meant lower food requirements. A shrew-sized mammal can survive on a few insects a day. It does not need hundreds of pounds of vegetation or meat. And in a world where the food chain has collapsed, where plants are dead and large prey animals are gone, needing almost nothing to survive is the ultimate advantage. The warm blood mattered too. Mammals generate their own body heat internally, maintaining a constant body temperature regardless of the external environment. Reptiles cannot do this. When temperatures drop, reptiles become sluggish, then torpid, then they die. Mammals can keep functioning in cold conditions, as long as they have enough food to fuel their internal furnaces. And there was one more thing. One more adaptation that seems almost trivially obvious now, but was, in the context of the extinction, perhaps the most important survival tool of all. Milk. Mammalian mothers produce milk, a nutrient-rich fluid secreted from specialized glands that feeds their young during the most vulnerable period of their lives. In a world where external food sources have collapsed, a mother mammal can still nourish her offspring from her own body's reserves. She becomes, in effect, a portable, self-contained food supply for the next generation. The babies do not need to find food. They need only to find their mother. This was not an adaptation that evolved in response to the asteroid. Mammals had been producing milk for tens of millions of years before the impact. But in the dark, starving, frozen world that followed the collision, milk was the difference between lineages that survived and lineages that did not. The mammalian strategy of intense parental care, of mothers investing their own bodily resources in the survival of a small number of offspring, turned out to be perfectly suited to a world in crisis. The dinosaur strategy, by contrast, the strategy of laying many eggs and providing relatively little parental care, was catastrophically vulnerable. Eggs need warmth. Hatchlings need food. In a world without warmth or food, eggs do not hatch and hatchlings do not survive. So the mammals lived. They huddled in their burrows through the long, dark winter, mothers nursing their young, feeding on whatever scraps they could find. Insects, which also survived the extinction in large numbers, provided a steady, if meager, food supply. Seeds, which could lie dormant in the soil for years, germinated when the skies finally cleared. And slowly, over thousands,
And then millions of years, the world began to recover. When the dust settled, literally, and the sunlight returned, the mammals emerged into a world transformed. The dinosaurs were gone. The ecological niches they had occupied, niches for large herbivores, large predators, fast runners, tree climbers, swimmers, flyers, were all empty. And the mammals, freed from 160 million years of dinosaur suppression, began to fill those niches with breathtaking speed.
The world that emerged from the impact winter was almost unrecognizable. The great forests that had covered the continents were gone, replaced by landscapes dominated by ferns, the first plants to recolonize disturbed ground, just as they still are today after forest fires. For thousands of years, fern spores dominated the pollen record, a phenomenon geologists call the fern spike, which serves as a reliable marker for the Chicxulub boundary layer in rock formations around the world. The oceans were equally devastated. The extinction of the ammonites, the disappearance of most plankton species, and the collapse of the marine food web left the seas eerily empty. It would take millions of years for marine ecosystems to recover their former diversity. The chalk deposits that give the Cretaceous period its name formed from the accumulated shells of trillions of tiny marine organisms, stopped forming abruptly at the extinction boundary. You can see this in the geological record as a sharp transition from white chalk to a thin layer of dark clay, rich in iridium, an element rare on Earth but common in asteroids. That clay layer, just a few centimeters thick, marks the moment when the Cretaceous world ended. Above the clay, the rocks tell a different story, a story of recovery, of new beginnings, of small creatures growing larger, filling empty niches, diversifying into forms that the Cretaceous world had never seen. The speed of mammalian diversification after the extinction was remarkable. Within the first 10 million years, mammals had produced the basic lineages that would dominate the Cenozoic era: the primates, the rodents, the carnivores, the ungulates, the whales. Body sizes increased dramatically. The earliest Cenozoic mammals were no larger than their Cretaceous ancestors, tiny and generalized.
But within a few million years, some lineages had grown to the size of modern wolves and bears. And within 10 million years, the first truly large mammals appeared. The ecological space vacated by the dinosaurs was enormous, and the mammals expanded into it with an exuberance that speaks to the extraordinary adaptability of the mammalian body plan. The warm blood, the fur, the milk, the large brains, the flexible behavior, all the traits that had been developed during 160 million years of living in the shadows turned out to be perfectly suited for building a new world. The evolutionary radiation of mammals after the Chicxulub impact is one of the most dramatic bursts of diversification in the fossil record. Within 10 to 15 million years, mammals had grown from shrew-sized generalists to a dazzling array of forms. Some lineages grew enormous, occupying the large herbivore niches vacated by sauropods.
Paraceratherium, the largest land mammal ever, stood 16 feet tall at the shoulder, a hornless rhinoceros relative that browsed on treetops the way sauropods once had. Other lineages returned to the sea, their limbs gradually transforming into flippers, their bodies becoming streamlined, their tails evolving into powerful flukes. They became the whales and dolphins, the new rulers of the oceans, filling the niches left empty by the mosasaurs and plesiosaurs. On land, carnivorous mammals diversified into every predatory niche. Saber-toothed cats, with their elongated canine teeth designed for puncturing the thick hides of large prey. Massive bear-like creatures. Packs of wolf-like hunters. And in the tropical forests of Africa, one particular lineage of mammals was developing a set of traits that would prove fateful. grasping hands with opposable thumbs, forward-facing eyes that provided binocular vision and depth perception, large brains relative to body size, social behaviors,
extended childhoods during which the young could learn from their elders. They were primates. And among the primates, one branch was about to face a crisis that would change everything. Not a global catastrophe this time, not a poison that covered the entire planet. Something much smaller, much more local. A forest drying up, a canopy thinning, a group of apes stranded on the wrong side of a geological fault line, watching the trees disappear around them. It does not sound like much. Compared to an asteroid or a supervolcano, a shrinking forest seems almost trivial. But this quiet, local catastrophe would turn out to produce the most consequential creature in the history of the planet. The seventh poison. The one that can read its own story. Chapter 7. The Last Poison, or The Next Medicine. The primate story is worth slowing down for because it illustrates something important about how evolution actually works.
It is not a ladder, with each species climbing toward some predetermined goal. It is a bush, constantly branching, with most branches leading to dead ends, and only a few, by luck and circumstance, persisting into the future. The earliest primates appeared roughly 65 million years ago, almost immediately after the asteroid impact cleared the dinosaurs. They were small, nocturnal, insect-eating creatures, probably resembling modern tree shrews. They had grasping hands, an adaptation for life in the branches, and forward-facing eyes which provided the depth perception needed to judge distances between branches accurately. These were not distinctively human traits. They were tree-climbing traits. Every adaptation that would eventually make us human started as an adaptation for something else entirely. Over the next 50 million years, the primate lineage diversified enormously. Some branches became the lemurs and lorises.
Others became the New World monkeys of South America, separated from their African relatives when the Atlantic Ocean opened up and the continents drifted apart. Others became the Old World monkeys and the apes. The apes, our own group, appeared roughly 25 million years ago. They were characterized by larger brains, the absence of tails, and more flexible shoulders that allowed a wider range of arm movement. The earliest apes lived in tropical forests and were probably fruit eaters, using their intelligence and dexterity to find and process food in the complex three-dimensional environment of the canopy. By about 14 million years ago, apes had diversified into many species across Africa, Europe, and Asia. But then, the climate began to change. The world was cooling, a long-term trend that would eventually lead to the ice ages. Forests shrank, grasslands expanded, and the apes, which had been a diverse and widespread group, began to decline. Most lineages went extinct. Only a few survived, in the remaining patches of tropical forest. Among those survivors were the ancestors of the modern great apes, orangutans in Southeast Asia, gorillas and chimpanzees in Africa. And one more lineage, ours. The split between the human lineage and the chimpanzee lineage occurred roughly 6 to 7 million years ago. The two groups are so closely related that their DNA differs by only about 1.2%. In terms of genetic distance, you are more closely related to a chimpanzee than a horse is to a zebra. The differences between us, language, technology, culture, the entire edifice of human civilization, are built on a foundation of genetic similarities so close that it is almost indistinguishable.
And that means the question of what made us different. What pushed one branch of African apes onto the path that led to stone tools and fire and language is a question about very small changes with very large consequences. The retreating forests,
the expanding savanna, the pressure to survive in an open, dangerous, resource-scarce environment. These were the forces that sculpted our ancestors into something new, something that the world had never seen before. Roughly 7 million years ago, the geological forces that had been reshaping the African continent for millions of years produced a dramatic change in the landscape of East Africa. Tectonic activity pushed great mountain ranges upward along the East African Rift, a massive crack in the continental plate that runs from modern-day Ethiopia down through Kenya, Tanzania, and into Mozambique. These mountains blocked the moist air currents that had been flowing in from the west, creating a rain shadow on their eastern side. The dense tropical rainforests that had covered much of East Africa began to shrink. The climate became drier. Trees died. Open grasslands, savanna, expanded into the spaces where forest had once stood.
And the primates that had been living in those forests, climbing through the canopy, eating fruits and leaves, secure in the three-dimensional world of the treetops, found their habitat disappearing. Some primate lineages retreated with the shrinking forests, following the trees. They became the ancestors of modern chimpanzees and gorillas, which still live in the remaining forests of Central and West Africa. But one lineage did not retreat. Whether by choice, by chance, or by the simple absence of forest to retreat into, they stayed on the edge. They found themselves in a new and terrifying environment, open grassland, a flat, exposed world with no trees to climb, no canopy to hide in, no fruit-laden branches overhead. A world where large predators, cats and hyenas and wild dogs, could see you from a distance, run you down with ease, and kill you without difficulty. By every measure of physical capability, these primates were absurdly ill-suited for life on the savanna.
They were slow. They had no claws, no fangs, no horns, no armor. They were smaller and weaker than the predators that hunted them. In a straightforward comparison of physical equipment, they should have been easy prey, quickly eliminated by natural selection. But they were not eliminated. And the reason they were not eliminated is the most consequential thing that has ever happened on this planet. They stood up. The transition to habitual bipedalism, walking upright on two legs as the primary mode of locomotion, was not sudden. It happened over millions of years through a series of intermediate forms. The earliest hominins, creatures like Sahelanthropus and Ardipithecus, were probably facultative bipeds, walking upright some of the time, but still spending significant time in trees. Over millions of years, the anatomy shifted. The pelvis widened and tilted. The spine developed an S-shaped curve to support the weight of the upper body over the hips. The feet lost their grasping toes and developed arches for efficient walking. The foramen magnum, the hole in the base of the skull where the spinal cord enters, migrated from the back of the skull to the bottom, allowing the head to balance directly on top of the spine. Standing upright did several things simultaneously. It freed the hands from the task of locomotion. Hands that had evolved for grasping branches could now be used for other purposes: carrying food, carrying infants, carrying tools. It also raised the head above the tall grass, allowing a better view of approaching predators. And it turned out to be a remarkably efficient mode of long-distance travel. Bipedal walking, while slower than quadrupedal running over short distances, uses less energy per mile. A human can outwalk almost any other animal over long distances, which, in the energy-scarce environment of the savannah, was a significant advantage. But the real transformation was not in the legs. It was in the hands, and what the hands eventually learned to do. The earliest stone tools in the archaeological record date to roughly 3.3 million years ago, from a site in Kenya called Lamekwi. They are crude, simple flakes struck from larger rocks, barely distinguishable from naturally broken stones. But they represent something without precedent in the history of life. An organism deliberately modifying a natural object to create a tool with a specific function. No other animal had ever done this in 4 billion years of evolution. Over the next 2 million years, tool technology improved gradually. The Oldowan tools, named after Olduvai Gorge in Tanzania, were more refined. Sharp-edged flakes used for cutting meat and scraping hides. Hammerstones for cracking open bones to get at the marrow inside. By 1.7 million years ago, Homo erectus had developed the Acheulean hand axe, a symmetrical, teardrop-shaped stone tool that required considerable skill and planning to produce. And Homo erectus did something else that was unprecedented. It controlled fire. The evidence for early fire use is debated among archaeologists, but there are sites in Africa and the Near East dating to around 1 million years ago that show clear signs of controlled burning. Hearths, charred animal bones, ash layers in cave deposits. By 500,000 years ago, the evidence is unambiguous. Fire was a regular part of hominin life. Fire changed everything. It provided warmth, extending the range of habitable environments into colder regions. It provided light, extending the useful hours of the day into the night. It provided protection from predators, since most animals fear fire. And, most profoundly, it provided the ability to cook food.
Cooking transforms food chemically, breaking down tough fibers, softening proteins, and transforming raw starches into forms that the gut can absorb far more easily. A cooked meal yields significantly more calories than the same food eaten raw. Richard Wrangham, a biological anthropologist at Harvard, has argued persuasively that the adoption of cooking was the key factor in the dramatic expansion of the hominin brain. The human brain is an extraordinarily expensive organ, consuming roughly 20% of the body's total energy budget, despite constituting only about 2% of body mass. Sustaining a large brain requires a reliable supply of dense, high-quality calories, and cooking provided exactly that. Over the next several 100,000 years, brain size in the hominin lineage increased dramatically. Homo erectus had a brain roughly 2/3 the size of a modern human's. By 300,000 years ago, a new species had appeared in Africa, with a brain fully as large as our own, Homo sapiens. And with that large brain came something that had never existed in 4.5 billion years of life on Earth: language. Not just the alarm calls and mating songs that other animals produce, but true, symbolic, open-ended language. The ability to refer to things that are not present, to talk about the past and the future, to describe things that do not exist, to tell stories, to share knowledge, to plan collectively, to imagine. Language transformed Homo sapiens from an intelligent animal into something qualitatively different. A species that could accumulate knowledge across generations, each generation building on what the previous one had learned, creating a ratchet of cultural complexity that no other organism has ever achieved.
A child born today inherits not just the genetic legacy of 4 billion years of evolution, but the cultural legacy of thousands of generations of human learning. Every language, every technology, every piece of knowledge, every story, every song, every scientific theory is part of that inheritance. And armed with language and tools and fire and the extraordinary flexibility of a large plastic brain, Homo sapiens spread across the Earth with a speed that no previous species had ever matched. Let me slow down here, because the emergence of Homo sapiens deserves careful attention. We appeared roughly 300,000 years ago in Africa. The earliest known fossils come from a site called Jebel Irhoud in Morocco, where skulls with distinctly modern features, a high forehead, a flat face, a rounded brain case, were found in deposits dated to about 315,000 years ago.
Other early Homo sapiens fossils have been found in Ethiopia, in South Africa, and at sites across the continent, suggesting that our species did not arise in a single location, but across a broad region of Africa, with different populations mixing and exchanging genes over long periods. For most of those 300,000 years, our ancestors lived as hunter-gatherers in small bands, rarely more than a few dozen individuals. They made stone tools. They hunted game and gathered wild plants. They probably had language or something close to it, based on the complexity of their tool-making and the evidence of long-distance trade in raw materials. But their impact on the planet was minimal. They were one species among many, living within the ecological limits of their environment, their population kept in check by the same forces that regulated every other animal: predation, disease, food availability, climate. And then something changed. Around 70 to 50,000 years ago, the archaeological record shows a sudden burst of behavioral complexity that some researchers call the Great Leap Forward. Though others argue the change was more gradual, cave paintings appeared, depicting animals and hunting scenes with remarkable skill and expressiveness. Jewelry was made from shells and bone. Musical instruments, simple flutes carved from bird bones, were crafted. Burial practices became more elaborate, suggesting beliefs about death and an afterlife. Trade networks extended over hundreds of miles, with raw materials and finished goods being exchanged between groups that may never have met face to face. Something had clicked. Whether it was a final neurological reorganization, a cultural innovation like the development of fully syntactic language, or some combination of factors, Homo sapiens had crossed a threshold.
We had become modern humans in the full behavioral sense: creative, symbolic, communicative, capable of abstract thought and long-term planning. Starting roughly 70,000 years ago, small bands of humans began migrating out of Africa. They crossed into the Middle East, spread into Asia and Europe, island-hopped through Southeast Asia into Australia, and eventually, during the last ice age, crossed the Bering Land Bridge into the Americas. Within about 50,000 years, humans had colonized every continent except Antarctica. They adapted to deserts and rainforests, to tundra and tropical islands, to mountains and coastlines. No environment was too harsh, no challenge too great. Where other species would have needed millions of years of evolutionary adaptation to colonize a new biome, humans did it in generations, using culture and technology instead of genetic change. And wherever they went, the world changed around them. The large animals that had never encountered human hunters, the mammoths and mastodons, the giant ground sloths, the saber-toothed cats, the giant wombats of Australia, the moas of New Zealand, disappeared. Whether humans hunted them to extinction directly or contributed to their decline through habitat modification and competition is debated, but the pattern is undeniable. The arrival of humans in a new region is consistently correlated with the disappearance of its megafauna. We were, from the very beginning, a transformative force. And then, roughly 12,000 years ago, in the fertile crescent of the Middle East, and independently in several other regions around the world, humans did something that changed the planet more profoundly than any event since the Great Oxygenation Event 2.5 billion years earlier. They planted seeds. Agriculture. The deliberate cultivation of plants and the domestication of animals for food. It sounds so simple.
But its consequences were staggering. For the first time, humans could produce food surpluses, more food than the immediate group needed to survive. Surpluses allowed populations to grow. They allowed some people to stop producing food and specialize in other activities, making tools, building structures, keeping records, governing, fighting. Villages became towns, towns became cities, cities became civilizations. The transition to agriculture is worth pausing on, because it was not, as it might seem, an obvious improvement in the quality of human life. In many ways, early farmers were worse off than the hunter-gatherers who preceded them. Hunter-gatherers typically had varied diets, consuming dozens of different plant and animal species. Early farmers ate mostly grain, a nutritionally inferior diet that led to widespread tooth decay, nutritional deficiencies, and shorter stature. Hunter-gatherers worked relatively few hours per day to meet their food needs. Farmers worked from dawn to dusk, ploughing, planting, weeding, harvesting, processing grain. Hunter-gatherers lived in small, mobile bands, where infectious disease could not easily spread. Farmers lived in dense, permanent settlements, surrounded by livestock and human waste, creating perfect conditions for epidemics. So why did agriculture win? Why did farming replace hunting and gathering almost everywhere on Earth? The answer is numbers. Agriculture could support more people per unit of land than hunting and gathering. A given area of farmland could feed 10 or 100 times as many people as the same area could support through foraging. The individual quality of life might have been lower, but the population density was vastly higher. And in a conflict between a small band of healthy, well-fed hunter-gatherers and a large, dense population of malnourished but numerous farmers, numbers prevailed. Agriculture was a trap, in a sense. Once a population adopted it and grew accordingly, there was no going back. There were too many mouths to feed with foraging alone. The population had committed itself to farming, and farming committed the population to staying put, to organizing, to building infrastructure, to all the complexities of settled civilization. And those complexities, problematic as they were, generated something unprecedented. Cumulative cultural evolution at scale. In a small hunter-gatherer band, knowledge is limited by what a few dozen individuals can remember and teach. In a city of 10,000 people, with writing and permanent records, knowledge can accumulate across generations indefinitely. Each generation adds to the store, techniques improve, technologies build on previous technologies, understanding deepens. Writing was invented to keep track of grain stores and property records. Mathematics was developed to measure land and predict the flooding of rivers. Metallurgy produced bronze, and then iron for tools and weapons. Organized religion provided social cohesion and moral frameworks for large groups of strangers living together. Governments formed to manage the complex logistics of agricultural societies. And all of this, all of recorded human history, from the first Sumerian city-states to the Roman Empire, to the Industrial Revolution, to the Internet, to this very moment, has unfolded in roughly the last 12,000 years.
12,000 years in a planetary history of 4.5 billion. If you compressed Earth's entire history into a single year, all of human civilization would fit into the last fraction of a second before midnight on December 31st. We are astonishingly recent arrivals. The ink on our entry ticket is not yet dry. And yet, in that infinitesimal sliver of time, we have changed the Earth more rapidly and more comprehensively than almost any force in its history.
We have cleared forests and dammed rivers. We have dug up and burned the fossilized remains of carboniferous swamps. Those ancient deposits of carbon that took hundreds of millions of years to accumulate and release their carbon back into the atmosphere in a matter of decades. We have altered the chemical composition of the atmosphere faster than any volcanic eruption in the geological record. We are driving species to extinction at a rate that some scientists compare to the great mass extinctions of the past. We are, in a very real sense, the sixth poison. The latest in a series of catastrophic disruptions that have reshaped the planet. But here is the question, and it is the question that this whole story has been building toward. Is this the same pattern? Does the rule still hold? Is the destruction we are causing going to clear the ground for something new, something more complex? Something we cannot yet imagine, the way every previous catastrophe did? Or are we different? Are we the first poison that might also be the cure? The first force of planetary destruction that is also aware of what it is doing, that can study its own impact, that can choose to change course? No previous catastrophe had a choice. The Siberian traps did not decide to erupt. The asteroid did not aim for the Yucatan. Cyanobacteria did not intend to poison the atmosphere with oxygen. These were blind processes, operating without awareness or intention. The destruction they caused was incidental, a side effect, not a decision. But we decide. We know what we are doing. We have the science to measure the consequences. We have the technology to develop alternatives. We have the historical knowledge of every previous catastrophe, every previous near miss, every previous recovery. We are the first force of nature that can read its own geological record and understand the pattern. And that, perhaps, is the real medicine. Not the destruction itself, but the awareness. The capacity to see the pattern from inside it and to act accordingly. Every previous poison became a medicine through blind, accidental processes that took millions of years. We might be the first one that can do it on purpose, deliberately, within a single generation. Or we might not. The story is not written yet. The pattern does not guarantee outcomes. It shows that destruction can create, but it does not show that it always does, or that it must. The Permian extinction killed 96% and left 4%. If it had killed 100, the pattern would have ended. The margin was thin, and it is thin now.
But the fact that you are here, lying in the dark, breathing oxygen that was once a poison, carrying mitochondria that were once a swallowed bacterium, built from calcium that Cambrian creatures first learned to extract from seawater, descended from terrified little mammals that survived a burning sky by hiding in burrows and nursing their young with milk. The fact that you exist at all, after 4.5 billion years of catastrophe and recovery, is evidence of something. Maybe not a guarantee, but evidence. Life, on this planet, has an extraordinary capacity to survive what should be unsurvivable, to find opportunity in devastation, to build complexity from wreckage. That capacity is in you. It is literally what you are made of.
Every cell in your body carries the legacy of every catastrophe and every recovery in the history of the Earth. Epilogue. Breath. And here is something that connects the very beginning of this story to its end.
The oxygen in your lungs tonight. The oxygen that cyanobacteria produced as a waste product 2.5 billion years ago. The oxygen that killed nearly every living thing on the planet. That oxygen is still flowing through the same cycle. Plants still produce it through photosynthesis. Animals still consume it through respiration. The balance between production and consumption is what maintains the 21% concentration that your lungs expect. If that balance shifted even slightly, if oxygen dropped to 15%, you could not sustain consciousness. If it rose to 35%, as it was in the Carboniferous, forests would burn at the slightest spark. You live in a narrow window, a thin band of chemical conditions that is maintained by the collective activity of every photosynthetic organism on the planet. The air you breathe is not a given.
It is a product, manufactured continuously by billions of tons of plant life, held in balance by processes that have been running since the Archean eon. And that balance is not guaranteed. It has been disrupted before, catastrophically, multiple times. The oxygen catastrophe, the snowball Earth, the Permian extinction. Each of these events involved a disruption of the atmospheric balance that nearly ended everything. The atmosphere is not a stage. It is a character, an active participant in the story, shaped by life and shaping it in return. And right now, for the first time in 4.5 billion years, one species has the ability to alter that atmosphere deliberately, to understand what it is doing, and, potentially, to choose a different course. So let us come back to where we started, back to the breath. Right now, your lungs are pulling in air that is about 21% oxygen.
That oxygen exists in the atmosphere because 2.5 billion years ago, cyanobacteria produced it as waste, and it killed nearly everything alive. The iron in your blood, the hemoglobin that carries that oxygen to your cells, contains iron atoms that were forged in the cores of massive stars that burned and exploded billions of years before the Earth existed. The calcium in your bones is there because 500 million years ago, Cambrian organisms learned to extract it from seawater to build armor against the predators that were trying to eat them. The mitochondria in your cells, the structures that are burning that oxygen right now to generate the energy that keeps you alive, are the descendants of a free-living bacterium that was swallowed by a larger cell roughly 2 billion years ago and never left. You are made of catastrophes, every one of them. The collision that gave us the moon, the oxygen that poisoned the old world, the ice that froze the planet,
The hunger that tore apart the Garden of Peace, the volcanic fire that killed nearly everything, the stone from the sky that ended the reign of giants. Each one of those events came within a margin of ending the story completely, and each one instead opened a door to something that could not have existed without the destruction that preceded it. 5 poisons, and you are the medicine. Or at least, you could be. The story is not finished. The Earth is 4.5 billion years old, and by the best estimates of astrophysicists, the Sun will continue to burn for another 5 billion years before it exhausts its hydrogen fuel and expands into a red giant. The story of life on this planet has a very long way to run, if life can continue to survive its own catastrophes. And right now, in this century, the latest catastrophe is us. We are changing the planet faster than any event since the Chicxulub impact. We know this because we can read the geological record.
We can see the pattern. We can measure the carbon in the atmosphere and compare it to the concentrations that preceded previous extinctions. We can count the species disappearing and compare the rate to the background extinction rate of the fossil record. The numbers are not ambiguous. Something is happening, something large. But here is what makes us different from every previous poison. We know. We are the first catastrophe that can look at itself in the mirror and recognize what it is seeing. The first force of planetary destruction that can also be a force of planetary repair. The cyanobacteria could not choose to stop producing oxygen. The Siberian volcanoes could not choose to stop erupting. The asteroid could not choose a different landing site. We can choose. Whether we will choose wisely, whether we will look at 4.5 billion years of evidence and act on what it tells us, is a question that does not have an answer yet.
The answer is being written right now by 8 billion people making decisions every day about how to live on a planet that has given them everything they have. But tonight, you do not need to answer that question. You do not need to solve anything. You just need to rest. Your body is doing what it has done since long before you were born, and will continue doing tonight without any instruction from you. Your heart is beating. Your lungs are filling and emptying. Your mitochondria are burning oxygen. Your cells are repairing themselves. The ancient machinery of life, 4 billion years old, tested by 5 catastrophes and refined by billions of years of evolution, is running quietly and efficiently in the dark. You are the product of every disaster and every recovery in the history of this planet. The collision, the poison, the ice, the hunger, the fire, the stone. All of it is in you. Every atom, every cell, every breath. And those breaths, those quiet, steady breaths you are taking right now, are made of the same oxygen that once killed nearly everything alive. The deadliest poison in the history of the earth, flowing in and out of your lungs, keeping you warm, keeping your thoughts running, keeping you here. The pattern holds. The poison became the medicine, and you are the proof. So let that settle. Let the long story of this planet soften into something quiet and warm. 4.5 billion years of fire and ice and catastrophe and recovery have led to this moment. To you, lying here, breathing, thinking, alive. The earth will keep turning. The story will keep unfolding. New chapters will be written by forces we cannot yet imagine. But right now, in this breath, in this heartbeat, in this quiet moment between waking and sleep, you are the latest verse in the longest poem the universe has ever composed. And that is enough. That is more than enough. Let your eyes close. Let the weight of the day lift. Let the ancient rhythms of your body carry you into sleep. The catastrophes can wait until morning. Tonight, you are safe. Tonight, you are the medicine. Rest now.